Hello there, and welcome to Science for Sleep, where complicated ideas are given enough room to slow down, settle into place, and become a little easier to follow. Tonight, we are leaving Earth behind and travelling much farther than any human being has ever gone. We're going beyond the moon, beyond the planets, beyond the familiar shape of the solar system, and out into the enormous distances between the stars. The question guiding us is simple to ask and surprisingly difficult to answer. If you travelled deep into space, became lost and decided to return home, could you actually find Earth again? At first, the answer seems obvious. Earth is a planet. Planets have locations. Spacecraft have navigation systems. We already send probes across the solar system, so surely a sufficiently advanced traveller could turn around, point toward home, and begin the journey back. That idea works reasonably well when you're still close to Earth. It also works when you're travelling within a mapped region of the solar system and receiving regular signals from known stations. The difficulty begins when those familiar supports are removed. Deep space does not provide road signs. There is no fixed grid printed across the universe. There is no universal north, no permanent centre, and no background that remains completely still while everything else moves across it. Even the word home becomes more complicated than it first appears. When you say that you want to return to Earth, do you mean the place where Earth was when you left? Do you mean the place where Earth is now? Do you mean the place where it will be when you finally arrive? Those are three different locations. If your journey lasts long enough, they may be separated by an extraordinary distance. Earth travels around the Sun at roughly 30 kilometers per second. The Sun moves around the centre of the Milky Way at more than 200 kilometers per second. The Milky Way itself moves relative to nearby galaxies and to the large-scale structure of the universe. While you're trying to work out where home is moving. It does not pause politely while you check the map. This is not a small inconvenience. It is the central navigation problem. Imagine leaving your house in a car, driving for several hours, and then discovering that the house has spent the entire time moving across the country. Finding it would require more than remembering the road. You would need to know its speed, direction, acceleration, and the forces acting on it. You would also need to know how your own motion had changed during the journey. In deep space, both you and your destination are moving through gravitational fields, and neither of you is following a perfectly simple path. There is another problem. You cannot look at Earth and see where it is at this exact moment. Light takes time to travel. When you look at an object, you see the light that has already completed the journey from that object to your eyes. The farther away the object is, the older the image becomes. From the moon, you see Earth as it was a little more than 1 second earlier. From Mars, depending on the positions of the planets, you may see Earth several minutes in the past. From a star 10 light years away, Earth appears as it was 10 years ago. If you were located 1,000 light years from home and had a telescope powerful enough to see the planet clearly, you would not be looking at present-day Earth. You would see Earth as it appeared 1,000 years earlier. The light reaching you would have left long before your arrival at that location. Earth would not actually be where the image appears to place it. It would have continued moving for 1,000 years. You could try to calculate its current position from the old light, but that would require detailed knowledge of its motion. You would need to account for the orbit of Earth around the Sun, the Sun's movement through the galaxy, the gravitational influence of nearby stars, the motion of the Milky Way, and the reference frame in which all of these quantities were measured. That last detail matters more than it may sound. A position in space is never simply a position. It is a position relative to something else. On Earth, we often ignore this because we have agreed upon useful systems. We use latitude and longitude. We measure altitude relative to sea level. We describe places using streets, borders, landmarks, and compass directions. These systems work because the surface of Earth gives us a shared reference. A house can remain at the same street address even though the planet beneath it is rotating. The address is attached to Earth, it moves with Earth. Nobody looks up from breakfast and complains that the kitchen has travelled several thousand kilometres since yesterday, although in an astronomical sense it has. In space, a coordinate system must also be attached to a chosen reference. You might define your position relative to the Sun, the centre of the Milky Way, a group of distant quasars, or the cosmic microwave background. Each choice can be useful, but none creates an absolute location that exists independently of everything else. The universe does not appear to contain a fixed platform from which all motion can be judged. This was one of the important lessons of relativity. Motion is measured relative to an observer or a reference frame. If two spacecraft pass one another in empty space, the other crew may describe the other spacecraft as moving. There is no nearby landscape to settle the disagreement. There is no universal speedometer floating outside the universe and announcing which spacecraft is really in motion. Acceleration can be measured. Rotation can be detected. You can feel the effect of an engine firing or determine that your spacecraft is turning. Constant velocity is different. If you're drifting smoothly through empty space with no view outside, there is no simple experiment that tells you your absolute speed through the universe, because physics does not provide an absolute state of rest in the ordinary sense. That means the first question in any deep space navigation problem is not merely, where am I? It is, where am I relative to what? Perhaps you're listening from a familiar room right now, with walls that stay where you expect them to be, and a floor that provides a dependable direction called down. Where are you listening from tonight? Are you at home, in a hotel, on a train, or somewhere else entirely? And if you had to describe your exact location without using the name of a country, a city, a street, a building, or any object attached to Earth, how would you do it? You might begin with the planet. You're somewhere on Earth. Then you might describe Earth's position relative to the Sun. After that, you could describe the Sun's position within the Milky Way. You could continue outward, placing the Milky Way within the local group of galaxies, the local group within a larger collection of galaxies, and that collection within the visible structure of the universe. Each answer depends on a larger reference. Remove the reference, and the location becomes incomplete. This does not mean navigation in space is impossible. Space agencies navigate with remarkable precision. Robotic probes have flown past distant planets, entered orbit around small bodies, landed on asteroids, and reached targets billions of kilometers away. These achievements are possible because the missions begin with detailed measurements, known starting conditions, carefully defined coordinate systems, regular observations, and continuous corrections. A spacecraft does not simply remember where Earth is, it repeatedly estimates its own position and velocity. It receives radio signals. It compares the observed positions of stars with stored models. Engineers track its path and update predictions. Small errors are found before they grow into large ones. Now remove the engineers, remove the radio contact, remove the familiar star patterns. Let the spacecraft travel for centuries, or perhaps thousands of years. Allow tiny measurement errors to accumulate. Place it in a region where nearby stars have shifted from the patterns recorded in its original maps. Let the gravitational influence of unseen objects alter its course. Then ask the traveller to find one small planet moving around one ordinary star among hundreds of billions of other stars. The problem changes. It is no longer similar to driving home with a damaged map. It becomes a problem involving reference frames, orbital mechanics, stellar motion, signal delay, uncertainty, gravity, and relativity. Each of those subjects creates a different way to become lost. Some of them are surprisingly ordinary. For example, a spacecraft does not need to make a dramatic mistake to miss Earth. A very small error in direction can become enormous across interstellar distances. If you point a spacecraft only slightly away from the correct path, the separation between the intended route and the actual route increases as the spacecraft travels farther. On a short journey, the error may be manageable. Across light years, it may cause the spacecraft to miss the entire solar system. Suppose an archer releases an arrow toward a nearby target. A tiny aiming error may move the arrow a few centimeters from the center. Now imagine that the target is not 20 meters away, but several trillion kilometers away. The same angular error produces a much larger miss. Deep space navigation is extremely sensitive to angles. The apparent positions of stars can help you determine orientation, but those stars are not fixed marks on a ceiling. They are moving through the galaxy. Some move slowly across our sky. Others have comparatively high proper motion, meaning their position changes noticeably over time when measured against more distant objects. The constellations look stable during a human lifetime because stars are very far away. The changes are usually too small to notice without precise measurements. Over tens of thousands of years, the shapes become different. Over hundreds of thousands or millions of years, familiar constellations may become unrecognizable. A traveller using an ancient map of the sky could search for a pattern that no longer exists. The stars would still be there, but they would no longer form the expected arrangement. It would be rather like returning to a city after every street, building and traffic sign had been slowly rearranged while you were away. The materials remain familiar, the layout does not. Even identifying the sun could be difficult from a great distance. To us, the sun is unmistakable. It dominates the sky, warms the planet, and makes looking directly at it a very poor recreational choice. From many light years away, however, it becomes another point of light. It is a G-type main sequence star, useful and important to us, but not unique in the galaxy. You could search for its spectrum, brightness, chemical composition, and movement, but many stars share similar properties. You would need enough information to distinguish the Sun from other candidates. You might look for the gravitational effects of its planets, or for artificial radio emissions from the solar system. Yet those signals become weaker with distance, and not every signal continues forever. Radio waves spread as they travel. Their energy is distributed across an expanding area. A transmission that is strong near Earth may become extremely faint after crossing interstellar space. Detecting it may require a large receiver, accurate knowledge of the frequency, and enough time to separate the signal from natural noise. There is also no guarantee that the signal tells you where Earth is now. A message carries information from the time and place where it was transmitted. If you receive a signal that has travelled for 500 years, it gives you evidence about the transmitter's position 500 years earlier. You must calculate how the source has moved since then. If the source changed velocity, entered a different orbit, or stopped transmitting, the problem becomes harder. If your own clock and navigation system have accumulated errors, even the age of the signal may not be known perfectly. Timekeeping is part of navigation. To calculate a position from motion, you need to know how much time has passed. To use pulsars as reference beacons, you need to measure the arrival times of their pulses. To predict an orbit, you need a reliable clock. To compare your observations with a stored map, you must know the date for which the map was accurate. A small clock error may sound harmless. Over long periods, it can corrupt estimates of velocity, distance, and signal travel time. Modern navigation systems on Earth depend heavily on precise clocks. GPS works by comparing the travel times of radio signals from satellites. A timing error of only a tiny fraction of a second can create a significant position error. The clocks on the satellites must also be corrected for relativistic effects, because their speed and their location in Earth's gravitational field cause them to tick at a different rate from clocks on the ground. Even finding a cafe on Earth quietly depends on Einstein. A deep space traveller would face the same physical principles without a convenient network of satellites surrounding the destination. The traveller would need to carry stable clocks, model relativistic corrections, identify reliable astronomical references, and maintain those systems over a journey that might last longer than a civilization. Equipment does not remain perfect forever. Sensors drift. Clocks accumulate error. Radiation damages electronics. Dust strikes surfaces at high speed. Stored information can degrade. A navigation system that begins with extraordinary accuracy may slowly become less certain. Uncertainty is unavoidable in measurement. Every observation has a limit. You can measure an angle very precisely, but not with infinite precision. You can estimate velocity, but there will be some range of possible values. You can predict the future position of an object, but the prediction will become less certain as time passes. That uncertainty spreads. If you know your speed only approximately, your estimated position becomes less reliable with every hour of travel. If an unknown gravitational pull changes your velocity by a very small amount, the effect may remain unnoticed at first. Centuries later, the difference between your calculated position and your actual position may be enormous. A navigation computer could still display coordinates with many digits. Computers are very good at displaying digits. That does not guarantee that the digits correspond to reality. The uncomfortable problem is not always having no answer. Sometimes it is having a very precise answer that is wrong. Deep space also contains objects that may be difficult to detect. Dark planets, faint stars, stellar remnants, gas clouds, and other masses can influence a trajectory through gravity. Most of the time, these influences are small, especially at great distances. Over long journeys, however, a small acceleration acting for a long period can change the path. Gravity never completely switches off. It weakens with distance, but every mass attracts every other mass. A spacecraft travelling between stars is affected by the gravitational field of the galaxy as a whole, along with local influences from stars and other objects. Its path is not a perfectly straight line drawn across an empty diagram. It is a trajectory through a changing gravitational environment. The same is true for Earth. Earth is falling around the Sun. The Sun is following an orbit through the Milky Way. The Milky Way is interacting gravitationally with nearby galaxies. Home is not sitting at a fixed coordinate waiting to be rediscovered. It is part of a moving physical system. There is something mildly unfair about this arrangement. The traveller must calculate a route toward a destination that is moving, while the traveller is also moving, while the reference objects used for navigation are moving, and while the information revealing those motions arrives late. It is rather more demanding than following a dropped pin on a phone. Still, the phrase, "you could never find your way home," needs to be handled carefully. Physics does not declare that returning to Earth is absolutely impossible under every imaginable condition. If you possess accurate maps, reliable instruments, sufficient energy, useful signals, and a well-understood starting point, you may be able to calculate a return path. The stronger claim is that a traveller who becomes genuinely lost in deep space may have no simple or guaranteed method of recovering the information needed to identify Earth and intercept it. Being lost does not merely mean facing the wrong direction. It means losing the connection between your observations and your original coordinate system. You may see stars but not know which stars they are. You may measure motion but not know your previous velocity. You may detect signals but not know when or where they were transmitted. You may build a new map of your surroundings, yet still lack the information needed to place that map within the larger galaxy. A map can describe everything nearby and still fail to tell you where home is. Imagine waking in an unfamiliar room with no windows. You can measure its length and width. You can map every piece of furniture. You can determine the local direction of gravity. You can learn the temperature, air pressure, and composition of the walls. None of those measurements necessarily tells you which building you're in. Local knowledge is not always enough to recover a global location. In deep space, the room is much larger. The furniture consists of stars, and the nearest person able to offer directions may be several light years away. Their reply, assuming they receive your question and know the answer, may take years to return. By then, both of you will have moved. Before we continue, I would be glad to know where you are listening from and whether you have ever been properly lost. Not temporarily unsure near a familiar street, but lost enough that the usual landmarks stopped helping. Perhaps it happened while driving, hiking, travelling in a new city, or walking through a building designed by someone with a personal objection to sensible corridors. That experience contains a small version of the deep space problem. You still have a location, of course, but you no longer know how your surroundings connect to the place you want to reach. The world has not vanished. The relationship between your map and the world has failed. If you find this slow journey through physics relaxing or interesting, you can support the channel with a like and a subscription. It helps these longer science discussions reach other listeners who enjoy learning, without being hurried through every idea. You're also welcome to leave your location in the comments, along with the local time, because a conversation about finding Earth seems like a suitable occasion to confirm that everyone is still on it. For now, you do not need to remember every number or technical term. The main idea is enough. Returning home from deep space would require more than finding a direction and applying thrust. You would need to reconstruct the physical relationship between yourself, Earth, the Sun, the galaxy, and the signals moving among them. That reconstruction begins with one of the simplest assumptions we make while standing on a planet. Here, you know which way is up. You know which way is down. You can stop moving relative to the ground, turn toward a destination, and describe your path with ordinary directions. The surface beneath you creates a stable local frame, even though Earth itself is moving rapidly. Far from planets and stars, those familiar directions disappear. Your spacecraft can rotate without you noticing immediately. It can drift at a constant velocity without producing any physical sensation. An object released from your hand will not fall to the floor unless the spacecraft is accelerating or producing artificial gravity. North and south no longer mean anything unless you define them relative to a particular axis. Even the idea of standing still must be replaced by a more careful question. Still relative to the spacecraft? Still relative to the Sun? Still relative to the center of the galaxy? Still relative to the average motion of distant galaxies? Each answer describes a different state of motion, and none is automatically the correct one. That is where the route home first begins to break down, because before you can decide where to go, you must decide what counts as rest, what counts as direction, and which part of the moving universe will serve as your map. On Earth, direction feels permanent because the planet provides a very convincing local environment. Gravity pulls objects toward the ground, so we call that direction down. The opposite direction becomes up. The planet rotates around an axis, giving us geographic north and south. The rising and setting of the sun help establish east and west. Once those directions are agreed upon, almost everything around us can be described in relation to them. A ceiling is above you. A floor is below you. One city lies north of another. A road runs east toward the coast. These descriptions remain useful because everyone involved is standing on the same rotating planet and treating its surface as the reference. The system works so naturally that it is easy to forget it is local. Down does not point in one universal direction. It points approximately toward the center of the mass that is producing the strongest nearby gravitational effect. For someone standing in London, down points toward the center of Earth. For someone standing in New Zealand, down also points toward the center of Earth, even though those two people are facing almost opposite directions in space. Neither person feels upside down. Both are standing normally because up and down are defined by the local gravitational field, not by a fixed orientation imposed on the universe. If you could look at Earth from a great distance, there would be no physical reason to draw the planet with the North Pole at the top. You could rotate the image in any direction, and the physics would remain unchanged. Maps usually place north at the top because of convention, not because the universe has marked one edge of the page as superior. Travel far enough from Earth, and the planet's gravitational influence becomes weaker. Another object may provide the dominant local field, or you may enter a region where no single nearby body creates an obvious down direction. Inside a freely falling spacecraft, you and everything around you accelerate together under gravity. Since the floor is not pushing upward against your feet, you experience weightlessness. This is why astronauts in orbit appear to float. They are not beyond Earth's gravity. Earth's gravity is still strong at the altitude of the International Space Station. The astronauts are falling toward Earth, but they are also moving sideways quickly enough that the curved surface of the planet falls away beneath them. They continue missing the ground. Orbit is a continuous fall with excellent timing. Inside the station, no direction is naturally down. A wall can serve as a floor if you place your feet against it. Equipment can be installed on every surface. Astronauts may work facing one another from what would appear, in a photograph, to be completely different orientations. Nobody falls onto the ceiling because the distinction between ceiling and floor has become a matter of design. A spacecraft travelling between stars would face the same issue, unless it were accelerating or rotating to create an artificial sense of weight. If the engines fired continuously, the rear of the spacecraft could behave like a floor. Objects would appear to fall toward it because the spacecraft would be accelerating into them. Stop the engines, and the apparent gravity would vanish. A rotating spacecraft could create another version of artificial gravity. As the structure turns, the outer wall would press inward on objects moving along a curved path. Occupants would feel pushed against that wall and could treat it as the floor. The direction called down would point away from the axis of rotation. This can be useful, but it's still not universal. The artificial down direction would exist because of the spacecraft's motion. Another spacecraft rotating around a different axis would define down differently. Turn off the rotation, and the direction disappears again. Even north becomes uncertain away from Earth. You could continue using Earth's geographic north, meaning the direction along the planet's rotational axis toward the North Pole. That is a valid convention, but it becomes less useful at great distances. You might instead define galactic north, a direction perpendicular to the main disk of the Milky Way. Astronomers use such coordinate systems because they help describe the positions of objects within the galaxy. Yet galactic north is not more physically correct than Earth north. It is simply attached to a larger structure. Another civilization living in a different galaxy might choose directions based on the plane of its own galaxy. Their north would not match ours. If they visited the Milky Way and asked which way was up, the honest answer would be that the question needs more information. Up relative to which gravitational field? North relative to which rotating body? Still relative to which frame? The absence of universal direction is inconvenient, but the absence of universal rest creates an even deeper problem. Suppose you're sitting inside a spacecraft with no windows. The engines are off. The craft is moving in a straight line at a constant speed. Nothing is shaking, accelerating, or rotating. You release a small object and it remains beside you. You perform experiments with light, springs, magnets, and mechanical devices. Everything behaves normally. Can you determine how fast the spacecraft is moving? Not without comparing it with something outside. You may be moving at 10 kilometers per second relative to one nearby star, 100 kilometers per second relative to another, and several hundred kilometers per second relative to the center of the Milky Way. All of those statements can be true at the same time. Velocity always requires a reference. A speedometer in a car measures speed relative to the road. An aircraft's ground speed is measured relative to Earth's surface, while its airspeed is measured relative to the surrounding air. Those values can differ because the atmosphere moves. A plane flying into a strong headwind may travel quickly through the air while making slower progress over the ground. In deep space, there is no road and almost no surrounding medium that can serve as a universal comparison. For centuries, some scientists thought that light might travel through an invisible substance called the luminiferous ether. If such a substance filled space, it could have provided a preferred state of rest. Earth's movement through the ether might have created an ether wind, rather like the airflow experienced by a moving vehicle. Experiments failed to find the expected effect. Einstein's special theory of relativity then removed the need for the ether entirely. The speed of light in a vacuum is measured to be the same by all inertial observers, regardless of their constant relative motion. This result is not intuitive because ordinary objects do not behave that way. Imagine standing on a moving train and throwing a ball forward. Someone beside you measures the speed of the ball relative to the train. An observer standing beside the track sees the ball moving at the speed of the throw plus the speed of the train. The velocities combine in the familiar way. Light refuses to follow that simple rule. If you switch on a lamp inside the moving train, both you and the observer beside the track measure the same speed for the light. The laws of physics adjust the relationships between distance and time so that this remains true. That adjustment leads to time dilation, length contraction, and the relativity of simultaneity. But the first lesson for navigation is more basic. There is no experiment performed inside a smoothly moving spacecraft that reveals a unique absolute velocity. You can detect acceleration because acceleration produces measurable effects. If the engines fire, you feel pressure against your seat. A suspended object shifts. Instruments called accelerometers record the change in velocity. If the spacecraft rotates, gyroscopes can reveal that rotation. Light beams sent in opposite directions around a rotating path may return at different times. Constant motion does not announce itself in the same way. A person sitting in a train at a station may briefly believe their own train is moving when the train beside it begins to roll. The visual background changes, but without another reference it may be difficult to decide which train is moving. Once the station platform becomes visible, the confusion ends because the platform provides a shared reference. Deep space has no station platform. Stars can serve as references, but they are moving. Galaxies can serve as references, but they are moving as well. The cosmic microwave background provides a particularly useful large-scale frame. This faint radiation fills the universe and is left over from its early hot state. By measuring a slight difference in its temperature across the sky, astronomers can determine how the solar system is moving relative to the frame in which that radiation appears most uniform. This is sometimes described as motion relative to the cosmic microwave background. It is extremely useful, but it does not restore absolute rest in the old Newtonian sense. The cosmic microwave background gives us a natural cosmological reference connected to the large-scale distribution of matter and radiation. It does not mean the laws of physics become different for an observer moving relative to it. A spacecraft could choose to match that frame. It could adjust its velocity until the cosmic background appeared nearly uniform in every direction. At that point, the crew could say they were at rest relative to the cosmic microwave background. Another crew could remain at rest relative to a nearby star. A third could remain at rest relative to the center of the Milky Way. None of them would violate physics. They would simply be using different frames. For a lost traveller, choosing the wrong reference frame can produce serious navigation errors. Suppose your records describe Earth's velocity relative to the Sun, but your current measurements describe your own velocity relative to the galactic centre. Those numbers cannot be compared directly. They must first be transformed into the same coordinate system. This is similar to combining instructions written in different languages, except the mistranslation may cause you to miss a planet by several billion kilometers. The problem becomes more complicated because direction also changes when reference frames rotate or accelerate. A rotating frame can create apparent forces. On Earth, the Coriolis effect influences winds, ocean currents, and long-range motion because the planet rotates. An object moving across the surface appears to curve relative to the ground, even though its path can be described differently from a non-rotating frame. Centrifugal effects also appear in rotating systems. Standing on a rotating platform, you feel an apparent push outward. From a non-rotating frame, your body is trying to continue in a straight line, while the platform constantly redirects your motion inward. Both descriptions can be used if the frame is clearly defined. A spacecraft using a rotating coordinate system may therefore observe objects following apparently curved paths. Its navigation computer must know whether the curvature comes from gravity, the spacecraft's rotation, or the mathematical choice of coordinates. Confusing one effect with another would produce incorrect corrections. Gyroscopes help preserve orientation. A spinning gyroscope tends to maintain the direction of its axis because angular momentum is conserved. Spacecraft use gyroscopes and related instruments to measure rotation and control attitude, which is the spacecraft's orientation in space. Attitude is not the same as position. You may know exactly which direction the spacecraft is pointing, while having no reliable idea where it is. A compass can tell a lost hiker which way is north, but it does not reveal which path leads back to camp. In deep space, even the equivalent of north must be defined, and knowing it still does not provide a location. A star tracker offers another method. It photographs the sky and compares the observed pattern of stars with a stored catalogue. Once several stars are identified, the spacecraft can calculate its orientation. This works very well when the catalogue is accurate and the stars appear in expected positions. Across very long periods, the stars move. Nearby stars also appear to shift depending on the spacecraft's location because of parallax. A pattern observed from one part of the galaxy may look different from the same pattern observed elsewhere. Some stars may be hidden behind dust, others may have changed brightness, exploded, or evolved beyond recognition. The navigation system must distinguish changes caused by time from changes caused by viewpoint. A familiar example of parallax can be seen by holding one finger in front of your face, close one eye, then the other. The finger appears to move relative to the background because each eye observes it from a different position. The finger has not actually jumped sideways. The apparent shift comes from the change in viewpoint. Astronomers use this effect to measure distances to nearby stars. Earth observes the same star from different points in its orbit around the Sun. The star appears to shift slightly against more distant background objects. The size of that shift reveals its distance. A lost spacecraft could use similar methods, but it would need to know enough about the objects being observed. A single image of the sky does not directly reveal distance. A bright point might be a nearby faint star or a far more luminous star at a much greater distance. Spectroscopy can provide clues. The colour and pattern of light from a star reveal temperature, chemical composition, motion along the line of sight, and other properties. Combining those measurements with apparent brightness and known stellar models can help estimate distance. Every estimate introduces uncertainty. If the spacecraft identifies one star incorrectly, the calculated frame may be distorted. If it mistakes a nearby object for a distant reference, parallax can alter the result. If its clock is wrong, the predicted positions of moving stars will also be wrong. Orientation, velocity, time, and position are linked. An error in one can spread into the others. This is why deep space navigation depends on repeated observations rather than a single dramatic moment of discovery. A spacecraft gathers data over time. It watches how objects move across the sky. It measures signal arrival times. It compares predicted and observed positions. It gradually reduces uncertainty. A completely lost traveller may not have the luxury of knowing which assumptions are safe. Even the spacecraft's own motion can make the sky appear different. Because light has a finite speed, moving observers see a slight change in the apparent direction of incoming light. This effect is called aberration. Earth's motion around the Sun causes stars to appear displaced by a small amount during the year. At ordinary spacecraft speeds, the effect is modest but measurable. At speeds approaching that of light, aberration becomes extreme. Light from much of the sky appears concentrated toward the direction of travel. Stars ahead become shifted and distorted into a narrower region, while the sky behind changes as well. Relativistic Doppler effects alter the observed frequencies. Light from the direction of travel may shift toward shorter wavelengths, while light from behind shifts toward longer wavelengths. Visible stars could change colour or move outside the visible range entirely. A traveller moving at a large fraction of the speed of light would not see the galaxy in the familiar form shown on the original map. The view would depend strongly on velocity. To reconstruct the ordinary appearance of the sky, the navigation system would need to estimate the spacecraft's motion and reverse the relativistic distortions mathematically. Yet estimating that motion may be one of the reasons the traveller is observing the sky in the first place. the problem becomes circular. You need the correct star map to calculate your motion, but you need your motion to interpret the star map correctly. With enough observations and a sufficiently accurate model, the circle can be broken. The system can test different possible velocities and positions until it finds a solution consistent with the data. Modern astronomy often solves problems in this way. The trouble is that more than one solution may initially fit limited observations. Additional measurements are needed to eliminate the incorrect possibilities. Meanwhile, the spacecraft continues moving. There is no option to pause in a universal resting place while the computer works. Turning off the engines does not stop the journey. It merely allows the spacecraft to continue along its current trajectory under inertia and gravity. Newton's first law tells us that an object remains at rest or moves with constant velocity unless acted upon by a net force. The wording includes both rest and constant motion, because in an inertial frame, the physics of those states is equivalent. A spacecraft drifting at 100 km per second does not gradually use up its motion. It does not require fuel to keep moving. Fuel is needed to change velocity. This is another point where experience on Earth can be misleading. Cars need engines to maintain speed because friction and air resistance continually slow them. Stop pressing the accelerator and the car eventually stops relative to the road. In space, where resistance is extremely small, a spacecraft can coast for a very long time. It does not coast relative to everything. It maintains its velocity relative to a chosen inertial frame until forces alter that motion. Gravity will usually alter it eventually. Passing near a star can change speed and direction. The galaxy's gravitational field guides long-term motion. Even tiny forces from radiation pressure, escaping gas, or uneven thermal emission can gradually modify the trajectory. If the traveller wishes to return home, they must first estimate this accumulated velocity. Position alone is not enough. Imagine locating Earth at a particular moment but failing to account for your sideways motion. You point the spacecraft directly toward the planet and fire the engines. During the journey, your existing lateral velocity carries you away from the intended line. Instead of reaching Earth, you pass through a different region of space. Orbital motion works this way constantly. A planet does not simply move in the direction it is facing, and a spacecraft cannot navigate by pointing its nose at the destination, as though driving along a straight road. The correct route depends on the full velocity vector, meaning both speed and direction, along with the gravitational fields along the way. Vectors are essential because movement in space has 3 spatial components. Saying that a spacecraft travels at 50 km per second is incomplete. 50 km per second in which direction? Relative to which frame? At what time? The same applies to Earth. To intercept the planet, you need its future position and future velocity in the chosen frame. Reaching the point where Earth is now would be useless if Earth has moved elsewhere by the time you arrive. This is familiar in a smaller form when throwing a ball to a moving person. You aim ahead, not at the person's current position. The faster the person moves and the longer the ball remains in flight, the farther ahead you must aim. Deep space interception follows the same principle, with the minor complication that the target is orbiting a star, the star is orbiting a galaxy, the traveller may be observing old light, and the ball has an engine. Before any route can be calculated, the traveller must rebuild a shared frame. They need a set of axes, a clock, a definition of distance, and a collection of objects whose motion is known well enough to serve as references. Only then can words such as here, there, toward, away, stationary and moving be translated into quantities the navigation system can use. The word here sounds precise because it refers to the place occupied by the speaker. Physically, however, here is an event in space-time. It includes a position and a time. Your current location is not merely a point in space. It is a point in space at this moment. A minute later, Earth has rotated. It has moved along its orbit. The solar system has advanced through the galaxy. The event that was here a minute ago is no longer your present event, even though the room looks unchanged. On ordinary scales, we ignore this because the coordinate system moves with us. The chair remains beside the table. The building remains on the street. The street remains within the city. Everything nearby shares much of the same motion. Deep space removes that convenience. Once the local frame has been lost, here cannot be connected to home until both are expressed within a common system. The traveller may be able to define a perfectly accurate local position, measure every nearby star, and describe every object within several light years, yet still have no idea where that region lies relative to the Sun. A coordinate is meaningful only after the reference frame has been chosen, and the choice determines how every position, distance, and velocity will be described. That may sound like a technical warning printed in the back of a physics textbook, but it reaches directly into the question of whether a lost traveller could ever find Earth again. To return home, the traveller needs an address. The problem is that space does not supply one. On Earth, addresses work because they are attached to a shared structure. A street address is tied to a road. The road is tied to a city. The city is tied to a country. Latitude and longitude are tied to the rotating surface of the planet. Even when we use satellite navigation, the reported position is expressed relative to Earth. The system feels absolute because the ground beneath us is stable enough for ordinary life, yet the entire structure is moving. Earth rotates once each day. It travels around the Sun once each year. The Sun moves through the Milky Way. The Milky Way moves relative to neighbouring galaxies. The address stays useful because the address moves along with the objects that define it. If your house were given coordinates in a frame fixed to the Sun rather than the surface of Earth, those coordinates would change constantly. If it were described in a frame fixed to the centre of the Milky Way, its motion would be more complicated still. The house itself has not become uncertain. Only the coordinate system has changed. This is the first important distinction. An object can exist at a definite location relative to a chosen frame without having an absolute position that belongs to it in every possible description. A chair can be 1 metre from a table, 3 metres from a wall, thousands of kilometres from the centre of Earth, and roughly 1 astronomical unit from the Sun. All of those statements refer to the same chair. None is the chair's single true position. Position is a relationship. It tells us where one thing is compared with something else. In elementary geometry, we often draw a grid and place a point on it. The horizontal and vertical lines appear to exist before the point arrives. We label the axes, choose an origin, and assign the point a pair of numbers. The process is clear and useful. The danger is forgetting that we created the grid. Real space does not arrive with graph paper already printed across it. There is no visible origin marked 0, 0, 0. There are no permanent axes stretching through the universe with small labels saying X, Y, and Z. Physicists and astronomers choose those structures because calculation requires them. The origin might be the centre of Earth, it might be the centre of the Sun, it might be the centre of mass of the solar system called the barycenter, it might be the centre of the Milky Way. The axes might be aligned with Earth's equator, the plane of Earth's orbit, the disk of the galaxy, or the positions of distant astronomical objects. Each choice has advantages. For a satellite orbiting Earth, an Earth-centered frame is convenient. For a spacecraft travelling between planets, a sun-centered frame may be better. For studying the motion of stars, a galactic frame becomes useful. No single system is best for every problem. This is similar to choosing a map. A subway map is excellent for finding train connections and terrible for judging the true distance between two buildings. A road map helps drivers but says little about elevation. A weather map displays pressure and temperature while ignoring the location of your preferred sandwich shop. Different maps describe different relationships. The map is not the territory, and the coordinate system is not space itself. If a traveller becomes lost, the problem is not solved merely by creating a new coordinate system. the traveller can place the spacecraft at the origin and describe every visible object relative to it. That creates a local map. It does not reveal where the map belongs within the galaxy. The spacecraft can say, this star is 12 light-years in that direction, and another is 20 light-years in the opposite direction. Those observations may be accurate, but unless the stars are identified, the traveller still does not know which way leads toward the Sun. It is possible to know where everything nearby is relative to yourself, while remaining completely uncertain about where you are relative to home. A person lost in fog can experience a simpler version of this. They may know that a tree is 10 meters ahead and a fence is 5 meters to the left. They can map the immediate surroundings with care. If they do not know which tree or which fence they are observing, the local map cannot be connected to the larger landscape. Deep space replaces the fog with distance. The nearby landmarks are separated by light years, and the larger landscape is changing while it is being observed. There is another difficulty hidden inside the word position. In modern physics, a position alone does not fully specify where something is. Time must be included. Suppose an astronomer says that Earth is located at a certain point in a sun-centered coordinate system. The statement is incomplete unless it includes the time of the measurement. Earth occupies that point briefly and then continues along its orbit. A useful address in space must therefore resemble an appointment. It needs both a place and a time. In relativity, a location at a particular time is called an event. The word does not necessarily mean something dramatic. A supernova is an event, but so is a clock hand reaching 12 or a particle passing through a detector. An event is simply something occurring at a particular position and time. Your current situation can be treated as an event. You're at a particular place at a particular moment in a particular reference frame. A few seconds later, you occupy a different event. This four-dimensional description is called space-time. 3 coordinates describe position and 1 describes time. Together they identify where and when something happens. The idea is essential for a traveller seeking Earth because the planet cannot be found by aiming at an old spatial coordinate. The route must lead to an event where the spacecraft and Earth occupy the same place at the same time. Passing through Earth's orbit is not enough. The spacecraft must arrive when Earth is there. If it arrives 6 months too early, Earth may be on the opposite side of the Sun. If it arrives thousands of years late, the entire solar system will have moved far along its galactic path. The destination is not a dot. It is a moving line through space-time. Physicists call the path of an object through space-time its world line. Earth has a world line, the Sun has one, the spacecraft has one. Returning home means arranging the spacecraft's future world line so that it intersects Earth's world line. This sounds more complicated than saying, yeah, fly back to the planet, but it expresses the real problem more accurately. The traveller must predict not only where Earth is, but where Earth will be when the journey is completed. That prediction depends on the chosen frame, the estimated travel time, the spacecraft's possible acceleration, and the gravitational forces affecting both paths. Even when all of those quantities are known, different observers may disagree about the coordinates assigned to the same event. This is not because one observer is careless. It is a result of relativity. 2 observers moving relative to one another use different measurements of space and time. They can disagree about the distance between events. They can disagree about the amount of time separating them. They can even disagree about whether 2 distant events occurred simultaneously. They still agree that an actual meeting either happens or does not happen. If the spacecraft reaches Earth, every observer can describe that intersection. What changes is the coordinate account of how and when it occurred. Consider 2 people watching a long train pass a platform. Lightning strikes the front and rear of the train. An observer standing midway along the platform may judge the strikes to be simultaneous, because the light from both reaches them at the same time. An observer sitting midway inside the moving train is travelling toward the light from one strike and away from the light from the other. Since both observers measure light at the same speed, the train observer does not assign the strikes the same time. The 2 observers disagree about simultaneity. That result matters because position is usually defined at a particular time. If observers disagree about which distant events are happening now, they can also disagree about the current arrangement of distant objects. There is no universal presence stretching across the cosmos on which everyone agrees. For ordinary navigation, the differences are often tiny. At the speeds of cars, aircraft, and most spacecraft, Newtonian ideas work extremely well. Engineers can use carefully defined corrections without turning every journey into a philosophical emergency. At interstellar distances and very high speeds, the differences become important. Imagine a traveller moving rapidly relative to Earth. The traveller asks, "Where is Earth right now?" Earth asks the same question about the traveller. Because simultaneity depends on the frame, the word now does not select the same distant slice of space-time for both observers. Each can calculate a valid position using their own coordinates. Neither has discovered an absolute present or an absolute position. The practical solution is agreement. Navigation systems specify a reference frame and a time standard. Every position is then reported within that shared convention. Space agencies use carefully defined frames based on astronomical observations and mathematical models. Planetary ephemerides provide predicted positions of the Sun, Moon, planets, and other bodies over time. These predictions allow spacecraft controllers to calculate trajectories and schedule observations. An ephemeris is rather like a timetable for objects that do not stop at stations and are all pulling on one another through gravity. The calculations can be extraordinarily precise, but they are not statements of absolute location. They are positions within an agreed framework, based on measurements and models. A lost traveller may possess an old ephemeris. That would be valuable, but only if the traveller knows the current time accurately and can determine the transformation between the spacecraft's present observations and the frame used by the ephemeris. If the ship's clock has drifted, the planets will not appear where expected. If the ship no longer knows its orientation, the directions will not match. If centuries have passed beyond the reliable range of the stored predictions, small uncertainties may have grown. The solar system is predictable, but not with infinite precision over unlimited time. Every model begins with measured initial conditions. Those measurements have uncertainty. Gravitational interactions are calculated with great accuracy, yet the system contains many bodies. Asteroids, comets, planets, moons, and smaller objects influence one another. For long enough predictions, tiny differences in starting values can grow. This does not mean Earth suddenly wanders to a random part of the galaxy. Its orbit remains physically constrained. It means the exact location along that orbit becomes harder to predict indefinitely without updated observations. The same is true on larger scales. The Sun's path around the Milky Way depends on the distribution of mass in the galaxy, including matter that is difficult to observe directly. Stars pass at varying distances. Molecular clouds and other structures contribute gravitational effects. The overall orbit can be modelled, but a lost traveller trying to project Earth's exact position over very long intervals would need detailed and current information. The traveller could search for the Sun directly, but that returns us to identification. Which point of light is the Sun? A coordinate catalogue gives each star a position, but those positions belong to a certain date and reference frame. Stars have proper motion, meaning they move across the sky relative to more distant objects. They also have radial motion toward or away from the observer. A catalogue is therefore not a collection of permanent pins, it is a moving model. To identify the Sun from far away, the traveller may need to compare observed stellar spectra, luminosities, motions, and relationships with surrounding stars. They may search for distinctive nearby systems, or for pulsars whose timing patterns act as recognizable signatures. Pulsars are rapidly rotating neutron stars that emit beams of radiation. As the beam sweeps past an observer, it can produce highly regular pulses. Different pulsars have different periods and patterns, allowing them to function as natural beacons. A famous diagram attached to the Pioneer spacecraft used pulsars to indicate the location of the solar system. Lines radiated from a central point, with binary numbers encoding the periods of selected pulsars. The idea was that an intelligent finder could identify the pulsars, determine their directions, and reconstruct the sun's location. It was a clever cosmic return address. Even that address changes with time. Pulsar periods gradually evolve. The stars move. The solar system moves. A reader must account for those changes to determine when and where the diagram was accurate. No address survives unchanged forever because the objects supporting it do not remain fixed. Distant quasars provide another useful reference. Quasars are extremely luminous active galactic nuclei located at enormous distances. Because they are so far away, their apparent motions across the sky are generally very small. Astronomers use them to establish stable celestial reference frames. From the perspective of navigation, they behave more like fixed points than nearby stars, but more like fixed is not the same as absolutely fixed. Their usefulness comes from distance and observational stability, not from being attached to a motionless background outside the universe. They define a practical frame, and practical frames are exactly what science needs. The lost traveller does not require metaphysical perfection. They require enough accuracy to identify a route. Still, the farther the journey and the longer the elapsed time, the more demanding the required accuracy becomes. Imagine that the traveller determines the direction of the sun with an angular error so small that it would be impressive in any laboratory. Across a few million kilometres, the resulting miss might be manageable. Across hundreds of light years, the same angular uncertainty can produce a separation larger than the solar system. This is because angular error grows into positional error with distance. A line aimed only slightly away from the target continues separating from the correct line as it extends. Deep space travel turns tiny mistakes into enormous misses. An absolute coordinate would seem to solve this. If Earth possessed a permanent location written into the structure of space, the traveller could simply navigate to that value. Physics offers no such label. The universe contains distances between objects, durations between events, patterns of motion, and geometric relationships. It allows coordinates to be built with extraordinary precision. It does not appear to assign each object an eternal address independent of every observer and every reference. This does not make reality vague. The distance between Earth and the Moon at a specified time can be measured. The trajectory of a spacecraft can be predicted. A radio signal can be timed. A collision either occurs or does not occur. The relationships are physical and testable. What disappears is the idea that one coordinate description must be the universe's own private version of the map. Coordinates are tools. A good tool preserves the relationships needed for the problem. A poor choice makes the equations difficult. Neither becomes part of the object being described. There is a useful comparison with temperature. A cup of tea has a temperature, but the numerical value depends on whether you use Celsius, Fahrenheit, or Kelvin. The tea does not change when the scale changes. The relationships between temperatures can be translated. Coordinates work in a broader way. Different observers can assign different numbers to the same event, and mathematical transformations connect the descriptions. Relativity tells us how to perform those transformations between suitable frames. For low relative speeds, the familiar Galilean transformations are often enough. At high speeds, Lorentz transformations account for the invariant speed of light and the linked behavior of space and time. The equations prevent coordinate freedom from becoming confusion. Observers may disagree about measurements, but their descriptions are not arbitrary. They are connected by strict physical rules. A lost traveller therefore has a possible strategy. First, construct a local frame. Measure orientation with stars, quasars, gyroscopes, or other references. Measure time with stable clocks. Estimate velocity through Doppler shifts. Signal timing and comparison with astronomical data. Identify enough objects to connect the local frame with a known galactic frame. Transform stored coordinates into that frame. then calculate Earth's future world line and design an intercept trajectory. Each step is physically possible in principle. Each step also depends on information the traveller may not possess. If the surrounding stars cannot be matched to the catalogue, the local frame remains disconnected. If the catalogue is too old, the matches may be ambiguous. If the velocity estimate is wrong, relativistic corrections and future predictions will be wrong. If Earth no longer emits detectable signals, the final identification becomes harder. The absence of absolute position does not forbid navigation. It removes the possibility of navigation without references. This distinction matters. A compass does not work because north is written into empty space. It works because Earth has a magnetic field. GPS does not work because every place owns an invisible coordinate. It works because satellites, clocks, radio signals, and mathematical models create a shared reference system. Take away the supporting structure, and the numbers lose their connection to the destination. A traveller in deep space must build that structure again from observations. At this point, the stars seem like the obvious solution. They cover the sky. They can be measured from great distances. Their spectra reveal useful information. Their patterns might allow the traveller to recognise the region and recover the route home. The coordinate system can be rebuilt only if the landmarks themselves can be identified, and the next difficulty begins when the traveller discovers that the stars have not remained where the map left them. From Earth, the night sky gives a strong impression of stability. The same constellations return with the seasons. The same bright stars appear in familiar parts of the sky. Orion rises, crosses the night, and sets. The plough keeps its recognisable shape. Polaris remains close to the direction of geographic north. People separated by centuries have looked upward and recognised many of the same patterns. This stability is real on the scale of a human lifetime, but it is not permanent. Stars only appear fixed because they are extremely far away. They are moving at high speeds through the galaxy, yet the distances separating them from us are so large that their apparent movement is usually slow. A car crossing a nearby street moves rapidly through your field of view. An aircraft at a high altitude seems to move more slowly, even though it is travelling much faster than the car. A distant mountain does not appear to move at all when you take a few steps sideways, although its apparent position would change if you travelled far enough. Distance reduces apparent angular motion. The stars are not attached to a solid surface. They are separate objects distributed through three-dimensional space. Some are relatively close to the solar system. Others are hundreds or thousands of light years farther away. Two stars that appear beside one another in a constellation may have no close physical relationship at all. They happen to lie along similar lines of sight from Earth. Move to another part of the galaxy, and those lines of sight change. A constellation that looks clear from Earth may stretch, collapse, or disappear entirely. Stars that once formed a recognisable outline may separate across the sky. Other stars, previously hidden behind them or too faint to notice, may become prominent. The constellation was never a physical object. It was a pattern created by a particular viewpoint. Imagine placing several lamps at different distances around a large room. From one doorway, they may appear to form a neat triangle. Walk to the other side of the room, and the triangle changes shape. One lamp moves visually between the others. Another appears farther away from the group. The lamps have not moved. Your perspective has. This apparent shift caused by a change in viewpoint is called parallax. Parallax is one of the most important tools in astronomy because it allows distance to be measured through geometry. As Earth travels around the Sun, our viewpoint changes. Astronomers observe a nearby star from one side of Earth's orbit, and then again roughly 6 months later from the opposite side. The nearby star appears to shift slightly against much more distant background stars. The angle is usually extremely small. A star with a parallax of 1 arcsecond lies at a distance of 1 parsec. A parsec is about 3.26 light years. The word itself comes from parallax of 1 arcsecond. Astronomers, like most specialists, occasionally name a unit by compressing an explanation until it sounds like something that might live under a bridge. An arcsecond is 1/3600th of a degree. That is a tiny angle. The nearest stars have parallaxes smaller than 1 arcsecond, so measuring them requires very precise observations. Space telescopes such as Gaia have measured the positions and motions of enormous numbers of stars with remarkable accuracy. These measurements allow astronomers to build a three-dimensional map of a large part of the Milky Way. For a spacecraft attempting to navigate home, such a map would be extremely valuable. The ship could observe nearby stars, measure their apparent directions and brightness, and compare them with the stored catalogue. The problem is that parallax depends on the observer's location. A star map made from Earth records the sky as seen from the solar system. A traveller located hundreds of light years away sees a different arrangement. Nearby stars may appear in very different directions. Even distant stars shift, although by smaller amounts. The traveller cannot simply hold up the old map and search for matching shapes. The map must be transformed to the new viewpoint. That transformation requires an estimate of the spacecraft's position, but the traveller is using the transformed star positions to determine the spacecraft's position. Once again, the calculation becomes circular. A navigation system can solve this by testing possible locations. It can choose a candidate position, calculate what the sky should look like from there, and compare that prediction with the actual observations. It can then adjust the candidate and repeat the process until the predicted sky matches the measured one. This method is similar to solving a large puzzle, in which the pieces keep changing size as you move around the table. With enough identified stars and accurate data, the solution may become unique. Without enough reliable matches, several locations might produce similar patterns. Brightness alone does not solve the problem, because apparent brightness depends on both a star's true luminosity and its distance. A nearby dim star can appear as bright as a much more luminous star located farther away. Dust complicates the picture by absorbing and scattering light. A star may appear fainter and redder than expected, because its light has passed through an interstellar cloud. The amount of dust along the line of sight changes with viewpoint, so a star that was clearly visible from Earth may be difficult to detect from another region. Spectroscopy provides better identification. When starlight is separated into its component wavelengths, it produces a spectrum. Dark and bright lines within that spectrum reveal the chemical elements in the star's atmosphere. The overall shape gives information about temperature. Other features help estimate surface gravity, rotation, magnetic activity, and evolutionary state. A star therefore carries something resembling a physical signature. The signature is not always unique. Many stars have similar temperatures and compositions. The Sun is important to us, but its spectrum is not a cosmic barcode possessed by no other object. A lost traveller would need to combine several measurements. The apparent direction, spectrum, luminosity class, motion, nearby companions and surrounding stellar pattern could all contribute to an identification. Binary stars may be especially useful. Many stars orbit in pairs or larger systems. The orbital period, separation, masses, and spectral features of such systems can provide a more distinctive set of properties than a single star alone. Variable stars could also act as markers. Some change brightness in regular patterns. Pulsating stars, such as Cepheid variables, have relationships between their pulsation periods and true luminosities, allowing astronomers to estimate distance. Pulsars offer even more precise timing patterns, although they are not visible in ordinary light and require instruments sensitive to radio waves, X-rays, or other parts of the electromagnetic spectrum. A traveller with a wide range of detectors would have a better chance of identifying the local sky than someone relying only on visible stars. Even after identification, the map must account for motion. The apparent movement of a star across the sky is called proper motion. It is usually measured as an angular change per year. A star with high proper motion noticeably changes position against the more distant background over decades. Barnard's star is a well-known example. It is relatively close to the solar system and has one of the largest known proper motions of any star. its apparent position shifts by more than 10 arcseconds each year. That movement is far too small to notice during a casual evening outside, but it becomes significant over centuries. After several thousand years, Barnard's star will occupy a very different part of the sky. Other stars move more slowly in angular terms, either because their true sideways velocity is smaller or because they are much farther away. Proper motion measures only the component of movement across our line of sight. A star can also move toward or away from us. This is called radial velocity. Radial velocity is commonly measured through the Doppler effect. When a light source moves toward an observer, its spectral lines shift toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. For visible light, these are often called blue shift and red shift. The names can be slightly misleading because the light does not always visibly turn blue or red. The shifts may be too small to notice by eye, and the star may emit strongly across many wavelengths. The important point is that the positions of known spectral lines change, allowing the motion along the line of sight to be calculated. Combine proper motion, radial velocity and distance, and you can estimate a star's three-dimensional velocity relative to the observer. That information allows astronomers to predict where the star was in the past and where it is likely to be in the future. For a lost traveller, this is essential. A catalogue listing only old positions is not enough. The system needs velocities so that the stellar map can be advanced to the current date. Suppose the spacecraft carries a map prepared 50,000 years earlier. A star that appeared near one constellation on the original map may now have moved into another region. Nearby stars with large proper motions may have shifted by several degrees. Constellation outlines may look stretched or broken. The traveller may initially conclude that the ship is in the wrong part of the galaxy, when the real problem is that the map is showing an earlier sky. Time and viewpoint create different distortions, and the navigation system must separate them. A change caused by viewpoint affects stars according to their distance and three-dimensional position. A change caused by proper motion depends on their velocity and the time elapsed. Both occur at once. The old Earth sky can therefore become unfamiliar even if the traveller returns to the solar system after a very long absence. The stars visible from home will have changed their positions while the traveller was away. The effect is slow by human standards, but interstellar journeys are not necessarily measured on human timescales. At the speeds reached by present spacecraft, travelling even to the nearest star would take tens of thousands of years. A mission across a substantial part of the Milky Way could take millions of years unless it moved at a significant fraction of the speed of light. During those periods, stars complete meaningful parts of their galactic orbits. Some approach the solar system and later recede. Stellar systems pass near one another. Clusters disperse. Massive stars evolve and explode. New stars form inside molecular clouds. The sky is not merely rearranging. Some of the lights themselves are changing. A bright blue star may survive only a few million years before ending its life as a supernova. A red giant may shed its outer layers and leave a white dwarf. A variable star may alter its behaviour. A binary system may merge. Dust may hide one region and reveal another. A navigation catalogue cannot assume that every landmark continues to exist in the same form. The most massive and luminous stars are easy to see from great distances, but they are also among the shortest lived. The dim red dwarfs that survive for enormous periods are harder to observe from across the galaxy. There is a trade-off between visibility and long-term stability. Distant galaxies and quasars remain useful because their immense distances make their angular shifts very small. They can provide orientation, but they are less useful for locating one small region inside the Milky Way. Knowing which way the distant universe lies does not automatically tell you which nearby star is the Sun. The traveller needs both a stable global frame and identifiable local landmarks. The Milky Way adds another complication, because stars do not all move together like dots painted on a rigid disk. The galaxy rotates, but not as a solid object. In a solid wheel, every point completes a rotation in the same amount of time. A point near the edge moves faster than a point near the centre because it must travel farther during one rotation. The Milky Way behaves differently. Stars at different distances from the galactic centre follow their own orbits, influenced by the distribution of visible matter and dark matter. Their orbital speeds do not decline in the simple way expected if most of the galaxy's mass were concentrated near the centre. This differential motion gradually changes the relationships between stars. The Sun takes roughly a couple of 100 million years to complete one orbit around the centre of the Milky Way. That period is sometimes called a galactic year. During one galactic orbit, the Sun does not remain beside exactly the same neighbouring stars. Each star follows its own path. Some overtake the solar system, others fall behind. The local stellar neighbourhood changes. The stars currently closest to us are not permanent neighbours. Proxima Centauri is the nearest known star to the Sun today, but another star may become closer in the distant future as stellar paths cross through the local region. Over long periods, the list of nearest stars is repeatedly rearranged. A map based on distance from the Sun must therefore include time. The nearest star is not a permanent title. The shapes of the constellations change for the same reason. The stars of the Plough, for example, are not all travelling in exactly the same direction at exactly the same speed. Several belong to a loose-moving group and share broadly similar motion, while others do not. Over tens of thousands of years, the familiar shape becomes distorted. Orion will also change. Its bright stars lie at very different distances and have different velocities. Some may evolve dramatically long before others. Polaris will not remain the North Star forever, although that change is not mainly caused by stellar motion. Earth's rotational axis slowly changes direction through a process called axial precession. The axis traces a broad circle over roughly 26,000 years, so different stars occupy the region near the North Celestial Pole at different times. A traveller carrying a simple instruction such as "find Polaris and use it as north" could be badly misled after enough time has passed. The star may still exist, but the relationship between Polaris and Earth's axis will have changed. This demonstrates how a navigation landmark can fail even when the object itself has barely moved. The observer's reference system changes too. Earth's orbit is not perfectly fixed. The planet's rotational axis changes. The solar system moves through the galaxy. Nearby stars drift. Every layer of the map has its own motion. A reliable navigation model must keep track of all of them. Light travel time makes the moving sky even harder to interpret. When you observe a star 100 light-years away, you see it as it was 100 years earlier. A star 1,000 light-years away appears 1,000 years in the past. Two stars visible beside one another may therefore be observed at very different stages of their histories. A sky image is not a picture of the galaxy at one shared moment. It is a collection of old light arriving from different distances. The farther the object, the older the information. If the traveller tries to reconstruct the current positions of stars, the system must account for the time taken by the light to arrive. A star observed 1,000 light-years away has continued moving for 1,000 years since emitting the detected light. The traveller can estimate its present location from its measured velocity, but the calculation requires accurate distance and motion data. Distance affects the delay, motion affects the correction. Both measurements contain uncertainty. A star moving across the line of sight changes its apparent direction. A star moving toward or away from the traveller changes its distance during the signal's journey. At very high relative velocities, relativistic effects must also be included. The observed sky is therefore a delayed and distorted record, not a live map. For navigation near Earth, signal delays can be measured and corrected. Deep space networks know when a transmission was sent and use accurate models of the spacecraft's trajectory. A lost traveller may not know the emission time of natural light or the exact history of the source. The ship sees where the star appeared to be when the light left it. The ship needs to know where the star is likely to be now. Then it must determine where the Sun is likely to be now. Finally, it must calculate where the Sun and Earth will be when the spacecraft reaches them. Each stage moves the target forward in time. A good stellar catalogue stores more than a photograph. It contains positions, distances, proper motions, radial velocities, spectra, magnitudes, variability, and uncertainties. With enough entries, a navigation system can search for a configuration that matches the observed sky. The matching process would not depend on one constellation. It would use a large network of relationships. It might compare the angular separation between many stars. It could examine spectral types, distances, and velocity patterns. It could identify pulsars by period. It could test which region of the galaxy would produce the observed combination. The more independent measurements available, the less likely it is that a false match will survive. Even so, a sufficiently long time or large displacement could make the original catalogue difficult to use. Predictions become less reliable as uncertainties accumulate. Some objects disappear or change. The apparent arrangement becomes increasingly unfamiliar. The ship may need to build an updated model from first principles. It could observe stars over several years to measure their proper motions. It could use parallax generated by the spacecraft's own journey to estimate distances. It could measure spectra and radial velocities. It could reconstruct the local three-dimensional structure of the galaxy. This would create an excellent map of the current neighbourhood. The remaining question would still be whether that neighbourhood could be connected to the old map containing Earth. The system would search for larger patterns that survive longer than constellations. It might identify globular clusters, dense ancient groups of stars orbiting the Milky Way. It might locate the galactic centre through radio and infrared observations. It could map the structure of the galaxy's disk and estimate its own position within it. These measurements would narrow the possibilities. Knowing that you are 30,000 light-years from the galactic centre and slightly above the galactic plane is more useful than knowing nothing. It is still not enough to identify one particular G-type star among billions. The local stellar arrangement must eventually be matched. This is where small uncertainties become dangerous. Suppose several stars are identified correctly, but their predicted positions are slightly wrong. The navigation system estimates the spacecraft's location with a small angular and distance error. From that estimate, it calculates the direction of the solar system. Across thousands of light years, the directional error can grow into a very large positional miss. The traveller might reach the correct general region of the Milky Way and still pass nowhere near home. The star map does not need to fail completely. It only needs to be slightly inaccurate for a very long distance. Aiming errors, clock errors, velocity errors, and imperfect stellar measurements all contribute. The ship's own motion continues throughout the calculation, and every correction changes the future route. The moving sky can tell a traveller where they might be, but it cannot provide perfect certainty. Every star is a measurement with a history. Every observed direction depends on viewpoint. Every position refers to old light. Every predicted location contains some uncertainty. Once the route is chosen, those uncertainties become physical separation. A fraction of a degree may appear harmless on a display. A tiny error in velocity may seem insignificant during the first day. Over an interstellar journey, the same mistakes continue growing until the spacecraft's calculated path and actual path no longer lead through the same region. The changing constellations are therefore not only a problem of recognition, they are the beginning of a larger problem involving accumulated error. Even after the traveller identifies the correct stars and reconstructs the general direction of the Sun, the journey home can still fail because a very small difference in position, speed, or angle becomes enormous when it is carried across light years. This happens because a spacecraft does not naturally follow the line drawn on a navigation screen. Once it has a velocity, it continues moving with that velocity unless a force changes it. The engines may be switched off, the crew may be asleep, and the control room may be extremely quiet, but the spacecraft does not stop. It continues along its trajectory. That is inertia. Newton's first law states that an object remains at rest, or continues moving at constant velocity unless acted upon by a net external force. Rest and constant motion are included in the same rule because neither is physically preferred. A spacecraft drifting smoothly through interstellar space does not need fuel to maintain its speed. It needs fuel only when the crew wants to change the speed or direction. This differs from most motion experienced on Earth. A bicycle slows when the rider stops pedaling. A car rolls to a halt when the engine no longer provides enough force to overcome resistance. A ball sliding across a floor eventually stops. These objects lose speed because friction and air resistance act on them. The ground creates the misleading impression that rest is the natural condition, and motion must be continuously supported. In space, there may be very little resistance. A spacecraft can coast for years, centuries, or much longer. Its motion does not become tired. Space does not gradually persuade it to stop. This is convenient for long journeys because the engines do not need to run continuously. It is also unforgiving because any unwanted velocity remains part of the motion until it is corrected. Suppose a spacecraft is intended to travel directly toward the solar system. Its navigation system calculates the correct direction, rotates the vehicle, and fires the engines. The burn is almost perfect, but not completely. The spacecraft leaves the maneuver with a tiny sideways velocity. At first, the error may be difficult to notice. Perhaps the intended forward speed is thousands of kilometers per second, while the unwanted sideways motion is only a few centimeters per second. Compared with the main velocity, that seems insignificant. A person walking slowly across a room moves faster. The trouble is that the sideways motion continues every second. At 1 centimeter per second, the spacecraft moves sideways by about 864 meters in one day. Over 1 year, the displacement becomes more than 300 kilometers. Over 1,000 years, it becomes more than 300,000 kilometers, roughly comparable to the distance between Earth and the Moon. That result comes from an error smaller than the speed of a slowly moving insect. Increase the sideways error to 1 meter per second, and after 1,000 years, the spacecraft is displaced by more than 30 billion meters, that is over 30 million kilometers. The error does not need to grow through any mysterious process. The velocity can remain perfectly constant. Time does the rest. This is why navigation requires more than aiming in approximately the right direction. The spacecraft must control its full velocity vector with extreme precision. A vector includes both magnitude and direction. Saying that the spacecraft travels at 1,000 kilometers per second gives only the magnitude. The navigation system must also know how much of that speed lies along each chosen axis. A tiny error in any component changes the future position. The same problem can be described as an angular error. Imagine drawing 2 lines from the spacecraft. One points exactly toward the future location of the solar system. The other differs by a very small angle. Near the starting point, the lines are almost indistinguishable. Farther away, the gap between them increases. At interstellar distances, a slight angular separation can become wider than a planetary orbit. 1 degree is obviously too large for precision navigation. Even 1,000th of a degree can be serious over a sufficiently long distance. A degree contains 60 arc minutes, and each arc minute contains 60 arc seconds. Astronomers often work with angles measured in arc seconds or even much smaller units, because distant targets demand that level of accuracy. If a spacecraft travels 1 light-year with an aiming error of 1 arc second, the missed distance will be roughly 1 astronomical unit. An astronomical unit is the average distance between Earth and the Sun, so an angular error that would appear extremely small on a screen can cause the spacecraft to miss Earth's orbit, by a distance comparable to the size of the orbit itself after only 1 light-year. Across 10 light-years, the same error produces a miss of roughly 10 astronomical units. Across 1,000 light-years, the displacement becomes roughly 1,000 astronomical units. The solar system may still lie somewhere in the general direction of travel, but somewhere in that direction is not sufficient when the target is a planet only about 12,700 kilometers in diameter. Even finding the Sun is not the same as intercepting Earth. A spacecraft could enter the outer solar system and still pass far above or below the plane of the planets. It could cross Earth's orbit when Earth is on the other side of the Sun. It could approach at a velocity too high to stop safely. A successful return requires control over position, direction, speed, and arrival time. Errors in these quantities interact. If the ship is slightly farther from the solar system than the computer believes, the journey takes longer. During that extra time, Earth moves farther along its orbit. If the ship's velocity is also slightly wrong, the predicted arrival point changes again. If the clock is inaccurate, the navigation computer may apply the correction at the wrong moment. One small mistake can therefore create another. This is not necessarily because the computer performs the mathematics incorrectly. It may be calculating perfectly from imperfect measurements. Every navigation estimate begins with observations. Sensors measure star directions, signal frequencies, acceleration, rotation, and elapsed time. None of these measurements has infinite precision. An instrument may report an angle as a certain value plus or minus a small uncertainty. A clock may gain or lose a tiny fraction of a second over a long period. An accelerometer may have a slight bias, meaning it consistently reports a value just above or below the true one. A small bias is especially dangerous because it accumulates. Imagine an accelerometer that reports a tiny acceleration even when none exists. The navigation computer may interpret that reading as a real change in velocity. It updates the estimated trajectory. Over time, the calculated position slowly separates from the actual position. The computer may still be internally consistent. Every displayed number may contain many decimal places. The crew may feel reassured by the impressive amount of precision. The decimals do not know whether the sensor was correctly calibrated. This problem is called inertial navigation drift. Inertial navigation systems estimate motion by measuring acceleration and rotation, then integrating those measurements over time. Acceleration is used to update velocity. Velocity is used to update position. Each integration allows errors to accumulate. A small acceleration error creates a growing velocity error. That velocity error then creates an even faster growing position error. If the system receives no external reference, the estimate drifts away from reality. Aircraft, ships, submarines, and spacecraft use inertial navigation because it operates without continuous contact with the outside world. Modern systems can be extremely accurate, but they still benefit from updates from GPS, stars, radar, radio beacons, terrain measurements, or other references. A lost interstellar spacecraft may have no convenient source of correction. It can observe stars, but identifying them may already be part of the problem. It can use pulsars, but the signals may be weak, the timing model may be old, and the spacecraft may not know enough about its own motion to interpret the arrival times immediately. Without reliable external measurements, the navigation solution becomes increasingly uncertain. Course corrections are therefore not optional additions to a long mission. They are part of the mission itself. Spacecraft traveling within the solar system regularly perform trajectory correction maneuvers. Engineers compare predicted positions with tracking data, estimate the difference, and command a small engine burn. These maneuvers may appear minor. A spacecraft can travel millions of kilometers between corrections, and the required change in velocity may be small. Yet correcting early prevents a small error from becoming a large miss. The timing matters. Suppose a spacecraft is drifting sideways relative to the desired path. Correcting that velocity near the beginning of the journey requires a modest change. Waiting until the spacecraft is close to the destination means the accumulated displacement is already large. The ship must then apply a stronger maneuver or approach from an inconvenient direction. In some cases, no available correction can recover the planned encounter. This is similar to walking across a large field toward a distant gate. If you notice immediately that you are heading slightly left, one small adjustment restores the route. If you continue for several kilometers before checking, the gate may be far to your right. The comparison becomes harsher in space because the gate is moving. Earth travels around the Sun while the spacecraft approaches. The correct path is not a fixed line toward the planet's current location. It is a carefully calculated intercept curve. The ship must aim for where Earth will be. A delay in the journey changes that future position. If the spacecraft arrives one day late, Earth has moved roughly 2.5 million kilometers along its orbit. That is an enormous distance compared with the size of the planet. Even an arrival error of 1 hour corresponds to Earth moving more than 100,000 kilometers along its orbital path. A clock error can therefore become a position error. Suppose the spacecraft's clock is wrong by 1 second. Earth moves about 30 kilometers along its orbit during that second. The Sun moves hundreds of kilometers through the galaxy during the same interval, depending on the chosen frame. For many purposes, a 1-second timing error is manageable. For a precise high-speed encounter, it may not be. The situation becomes more demanding if the spacecraft is travelling at a large fraction of the speed of light. At 10% of light speed, it covers roughly 30,000 kilometers every second. A timing mistake of 1 second then shifts the spacecraft's expected position by about 30,000 kilometers along its path. The speed improves travel time but reduces tolerance for error. Fast spacecraft also require more energy for correction. Changing the velocity of a massive vehicle by even a small amount can demand significant fuel or another source of propulsion. The relationship is especially challenging because the spacecraft must eventually slow down. A vehicle moving quickly toward the solar system cannot simply arrive and stop. It must remove the velocity gained during acceleration. If the braking maneuver begins too late, the spacecraft may pass through the system before losing enough speed. Interstellar travel therefore involves a velocity budget. Engineers often describe planned changes in velocity using the term delta V. It is not simply the amount of fuel carried, although fuel and propulsion determine how much delta V is available. It represents the total ability to change velocity through maneuvers. Every correction uses part of that budget. A journey designed with no allowance for error would be dangerously fragile. The spacecraft needs enough reserve to adjust for imperfect measurements, unexpected forces, and changes in the target prediction. Too many corrections may leave insufficient capability for braking or final approach. The lost traveller faces an additional difficulty because the direction of the required correction may be uncertain. A burn performed using the wrong navigation solution can make the error worse. If the ship's estimated position lies to one side of the actual position, the computer may command a correction toward the wrong side. The maneuver moves the spacecraft farther from the correct trajectory, while the display reports improvement. This is the space travel version of confidently following a navigation app after it has placed your car on a parallel road. The difference is that turning around may take several months and a very large amount of energy. Redundant sensors help reduce such risks. Several independent instruments can measure the same quantity. If one disagrees with the others, the navigation system can identify a possible failure. Yet redundancy does not eliminate every problem. Multiple sensors can share the same design flaw. Radiation can affect several systems. A stored star catalogue can be wrong for every camera using it. The strongest navigation method combines different types of evidence. The spacecraft can compare inertial measurements with star positions, pulsar timing, radio signals, and observations of planetary bodies. Each source constrains the possible position and velocity in a different way. This is often handled through estimation techniques such as filtering. A navigation filter does not assume that one measurement is perfect. It combines a model of the spacecraft's motion with new observations. Each measurement is weighted according to its expected uncertainty. The result is an estimated state, including position and velocity, along with a range of uncertainty. When new data arrives, the estimate is updated. The uncertainty matters because it tells the system how much confidence to place in the predicted path. A route shown as a single thin line can be misleading. A more honest display would show a growing region containing many possible trajectories. Over time, that region may expand. If the spacecraft has not received an external correction for centuries, its actual position may lie anywhere within a large volume. The computer does not know which point inside that volume is correct. This is sometimes described using an uncertainty ellipsoid. The possible positions form an elongated three-dimensional region with different amounts of uncertainty along different directions. The region may be narrow across the direction of travel but very long along it, or the opposite, depending on the measurements. For an interstellar journey, even the narrow dimension may eventually become millions of kilometers wide. The traveller may still know the general part of the galaxy occupied by the spacecraft. That is not enough for a direct return to Earth. Aiming for the solar system requires the uncertainty region at arrival to be much smaller than the region the spacecraft can search or correct within. The ship could deliberately aim for the Sun rather than Earth, because the Sun is much larger, more massive, brighter and easier to detect. This improves the problem but does not remove it. The Sun's physical diameter is about 1.4 million kilometers, far larger than Earth's. Its gravity also affects approaching objects across a much larger region. A spacecraft reaching the inner solar system could then navigate toward Earth using local observations. Yet the ship must avoid entering the Sun, passing too close at excessive speed, or approaching from a trajectory that cannot be converted into a safe orbit. The target becomes easier to find but still requires control. A spacecraft might use the Sun's gravity to bend its path. Gravity assists are common in solar system missions. A spacecraft passes near a moving planet and exchanges energy and momentum with it, changing speed and direction relative to the Sun. For a lost traveller, a gravitational encounter might provide a useful correction without consuming as much propellant. It might also make the situation worse if the approach is not calculated accurately. A small difference in the incoming trajectory can produce a large difference in the outgoing path. Pass on one side of a body and the spacecraft turns one way. Pass on the other side and it turns another. Approach too closely, and the vehicle may collide or experience damaging tidal forces. Gravity assists reward precision and punish improvisation. Interstellar space also contains small forces that are easy to ignore during short missions. Photons carry momentum, so light can push on a spacecraft. This radiation pressure is weak, but it acts continuously. A spacecraft with a large sail is designed to use this effect. A conventional spacecraft may experience it as a disturbance. Thermal radiation can also produce thrust. If one side of the spacecraft emits slightly more heat than the other, the outgoing photons carry momentum and create a small force in the opposite direction. Gas leaking from a tank or material slowly evaporating from a surface can produce another tiny acceleration. A collision with dust changes momentum as well. Most individual impacts are small, although at very high speed they can damage the spacecraft and alter its mass distribution. Each effect may be negligible for a day and meaningful over centuries. The Pioneer anomaly provides a useful example of how small forces can complicate navigation. The Pioneer 10 and 11 spacecraft appeared to experience a tiny, unexplained acceleration toward the Sun. For years, researchers investigated possible causes. The effect was eventually understood mainly as a result of uneven thermal radiation from the spacecraft. Heat leaving the vehicles produced a small recoil force. The acceleration was extremely weak, but careful tracking detected it across long periods. A force too small for any crew member to feel was large enough to matter in precision navigation. A traveller crossing light years would have to model such forces for much longer. The spacecraft itself may also change. Fuel is consumed, components move, rotating machinery stores angular momentum, micrometeoroid impacts alter surfaces, repairs change the distribution of mass. The navigation model must be updated as the vehicle ages. Even turning the spacecraft can affect the route slightly. Internal movements usually preserve the total momentum of the isolated vehicle, but using thrusters, releasing material, or changing the direction of emitted radiation produces external effects. A correction system must know what every maneuver actually achieved. Engines do not deliver perfectly identical thrust every time. Their performance depends on temperature, pressure, wear, and fuel conditions. A commanded burn of exactly 1 meter per second may produce slightly more or less. After the burn, the system must measure the result. Without measurement, correction becomes guesswork. The long journey home is therefore not one decision followed by a quiet coast. It is a continuous cycle of observation, prediction, maneuver, and verification. The spacecraft estimates where it is. It predicts where the solar system will be. It calculates a correction. It performs the burn. It measures the new trajectory. Then it repeats the process. As the destination becomes closer, the required navigation can become more precise because the sun grows brighter, planetary signals may become detectable, and the geometry of the solar system becomes easier to observe. The difficult part is reaching that region closely enough for local navigation to take over. If the spacecraft misses by several light years, the sun may remain just another faint point. The traveller might continue past the correct part of the galaxy without realising how close the route came. A near miss on a galactic map can still be an enormous failure. There is also no simple visual cue showing that the spacecraft is drifting away from the planned line. Empty space provides no lane markings. The crew cannot look out of the window and notice that the ship has moved slightly left of the route. Deviation is known only through measurements and calculations. The stars ahead do not necessarily appear to slide dramatically. Their immense distance makes small lateral movement difficult to detect. By the time the change is obvious, the accumulated error may already be large. This is why precision is not merely a matter of having better instruments. It is a matter of checking often enough that errors remain correctable. A small error corrected early is inexpensive. The same error discovered late may require a large maneuver. If it is discovered after the spacecraft has exhausted its propulsion reserve, it becomes permanent. Inertia preserves the mistake with the same reliability that it preserves the intended motion. The universe does not distinguish between a carefully planned velocity and an accidental one. Once established, both continue according to the same laws. For the lost traveller, this creates a difficult balance. The ship must travel quickly enough to make the return possible within a useful time, but greater speed increases the distance covered during every timing or guidance error. The ship must conserve fuel, but delaying corrections allows errors to grow. It must trust its instruments, while remembering that those instruments may be the source of the drift. A route through space is often drawn as a straight line because a straight line is easy to understand. Place the spacecraft at one end, place the destination at the other, and connect them. If nothing interferes, the shortest distance between those 2 points is clear. Gravity interferes. Every star, planet, moon, asteroid, cloud of gas, and concentration of dark matter contributes to the gravitational field through which the spacecraft moves. Most of those individual pulls are weak at great distances. They are still present and they continue acting for as long as the spacecraft remains in the field. The ship may begin on a trajectory aimed carefully toward the predicted location of the sun. As it travels, a nearby star pulls it slightly to one side. The wider gravitational field of the Milky Way changes the motion more gradually. A distant object may contribute an effect too small to detect at first. By the time the spacecraft reaches the region where the solar system was expected, the route may no longer pass through it. Gravity does not need to push the ship dramatically off course. As with a small velocity error, a tiny acceleration can matter when it acts for a long time. Newton described gravity as an attractive force between masses. The strength of that force increases with the masses involved and decreases with the square of the distance between them. Double the distance between two objects, and the gravitational force becomes 1/4 as strong. Increase the distance by a factor of 10, and it becomes 100 times weaker. The inverse square relationship allows gravity to fade rapidly with distance, but it never reaches a sharp boundary where it switches off completely. Earth's gravity extends beyond the moon. The sun's gravity extends beyond the planets. The Milky Way's gravity influences stars, gas, clusters, and spacecraft throughout the galaxy. A spacecraft travelling far from any planet is not in a place without gravity. It is in a place where many gravitational influences may be weak and distributed. Inside the solar system, the Sun usually provides the dominant gravitational effect. A spacecraft moving between planets follows an orbit around the Sun, even when its trajectory does not form a closed circle or ellipse. An orbit does not always mean repeatedly circling an object. It can also be an open path that passes once through a gravitational field and continues outward. A comet approaching the Sun may follow a long elliptical orbit and return after many years. Another object moving quickly enough may follow a hyperbolic path, swing around the Sun, and leave the solar system permanently. The shape depends on the object's position, velocity, and total orbital energy. This is why pointing directly at a destination is rarely the correct way to travel through a gravitational system. If a spacecraft aims straight toward a planet, both the planet and the spacecraft continue moving while gravity curves their paths. Interplanetary missions are planned as transfers between moving orbits. The spacecraft leaves one orbit around the Sun and enters another path designed to meet the target planet later. The target is not where it appears when the maneuver begins. A mission to Mars, for example, does not aim at the bright point where Mars is currently visible. It aims for a future meeting place. During the journey, Mars moves around the Sun, Earth continues around the Sun, and the spacecraft follows its own curved solar orbit. The route may look like an arc rather than a direct line. A traveller returning from deep space faces the same principle on a much larger scale. The solar system is moving through the gravitational field of the Milky Way. The spacecraft also follows a galactic trajectory. Returning home requires changing one curved path into another that will eventually intersect it. There is no fixed galactic floor across which the ship can draw a ruler. If the spacecraft is thousands of light years away, the gravity of the Milky Way affects the entire journey. The ship and the Sun may orbit the galactic centre at different distances, different speeds, and different inclinations. The Sun travels around the galaxy at roughly a few hundred kilometres per second. Its orbit is not a perfect circle, and it also moves slightly above and below the main galactic plane over long periods. A lost spacecraft located elsewhere in the Milky Way will have its own combination of radial, sideways, and vertical motion. Even if it knows the current direction toward the Sun, firing its engines along that line does not automatically place it on an intercept trajectory. Its existing galactic motion remains. Suppose the spacecraft and the Sun are both moving around the galactic centre, but the spacecraft is on an orbit closer to the centre. Objects in the different galactic regions can have different orbital periods and paths. The ship may advance around the galaxy at a different rate from the Sun. A return manoeuvre must account for this differential motion. It is similar to transferring between two vehicles moving around a circular track. Although the galactic version has no painted lanes, takes millions of years, and includes several 100 billion other objects contributing to the gravitational field. The spacecraft might attempt to cancel its current galactic velocity and then accelerate toward the Sun. That would require an enormous amount of energy. It may also be unnecessary. A more efficient route would use the ship's existing motion and alter it enough to create an intersection with the solar system's future path. Orbital mechanics often rewards indirect-looking maneuvers. A spacecraft may initially accelerate in a direction that does not point toward the destination, because the goal is to reshape the entire orbit. To move farther from the Sun, a spacecraft usually increases its sideways orbital speed. That raises the opposite side of its orbit. To move inward, it reduces orbital speed, allowing it to fall closer to the Sun. The same general logic applies in a galactic gravitational field, although the mass distribution is far more complicated than one central object. The Milky Way contains stars, gas, dust, a central bulge, a dark matter halo, and a supermassive black hole at its centre. The black hole is important near the centre, but it does not dominate the motion of the entire galaxy in the way the Sun dominates the solar system. Most stars in the galactic disk orbit according to the combined gravitational influence of matter distributed across a vast region. A lost traveller would need a model of that distribution to predict the ship's future trajectory accurately. Visible matter is only part of the problem. Observations of galactic rotation indicate that galaxies contain much more gravitating mass than can be explained by visible stars and gas alone. This additional component is called dark matter. Dark matter does not emit, absorb, or reflect light in the ordinary way, so the traveller cannot simply photograph it. Its presence is inferred from gravitational effects. A navigation system may map stars perfectly and still miscalculate the galactic field if its dark matter model is incomplete. The ship would appear to drift away from the predicted path, even though the engines and instruments were functioning correctly. The failure would lie in the gravitational map. Models can be improved by observing the motions of many stars. Their velocities reveal information about the mass distribution holding them in orbit. A traveller could gradually reconstruct the local gravitational potential by measuring how nearby objects move. That process takes time. It also requires separating the motion of the stars from the motion of the spacecraft. Every observation is made from a platform that is itself accelerating through the same galactic field. Local gravity can be measured with instruments, but a uniform gravitational field creates a subtle difficulty. In a freely falling spacecraft, the crew may feel weightless, even though gravity is changing the ship's trajectory. The ship, crew, equipment, and any loose objects all accelerate together. No one is pushed against the floor because there is no floor preventing the fall. An accelerometer attached to the spacecraft does not necessarily register ordinary gravitational free fall as the kind of acceleration felt during an engine burn. This distinction is central to general relativity, but it already matters for navigation. The crew cannot rely on physical sensation to know how gravity is bending the path. They must observe the changing positions of external objects or compare the spacecraft's trajectory with a model. Tidal effects can reveal differences in gravity across the ship. If the gravitational pull is slightly stronger at the front than at the rear, free objects may slowly separate. Near a planet, star, or black hole, these differences can become large. Far from concentrated masses, the tidal effects may be tiny. The spacecraft can be turning gradually through the galaxy without the crew feeling any obvious force. This makes gravity easy to underestimate. A constant engine acceleration produces a clear pressure against the seats. Galactic gravity may alter the route continuously while everything inside remains calm. The navigation computer must calculate what the crew cannot feel. Passing stars create more local disturbances. A star does not need to lie directly on the route to bend the spacecraft's path. Gravity acts across distance, so the ship begins responding before the closest approach and continues responding afterward. The resulting trajectory resembles a smooth curve. If the spacecraft passes behind the star relative to its direction of motion, the star's gravity pulls it inward, changing both direction and speed relative to the chosen frame. The effect depends on the star's mass, the closest approach distance, and the spacecraft's incoming velocity. A slow spacecraft passing near a massive star can be deflected strongly. A very fast spacecraft is exposed to the strongest part of the field for less time and may experience a smaller directional change, although high speed creates its own navigation and energy problems. Approach distance is critical because gravity strengthens rapidly as separation decreases. A small error in the predicted closest approach can therefore produce a much larger error in the outgoing trajectory. This is the basis of gravitational assists. Space missions deliberately pass near planets to alter velocity. A moving planet pulls on the spacecraft, and the spacecraft pulls on the planet. Momentum and energy are exchanged, although the planet's change is far too small to notice in most missions. Relative to the planet, the spacecraft may leave with nearly the same speed it had on arrival, but its direction changes. Relative to the Sun, that change can increase or decrease the spacecraft's speed. This method has allowed probes to reach distant parts of the solar system without carrying enough fuel to perform every velocity change directly. A lost traveller might use stars or planets in a similar way. A carefully planned encounter could bend the trajectory toward the solar system or help reduce speed before arrival. The word carefully is doing considerable work. The required accuracy would be severe. If the spacecraft approaches the wrong side of a star, the gravity assist turns it away from home. If it passes too far out, the deflection is too weak. If it passes too close, heat, radiation, tidal forces, or direct collision become serious concerns. The star is not a convenient corner around which the spacecraft can steer at the last moment. The incoming path determines the outgoing one long before the closest approach. A navigation error made light years earlier may decide which side of the star the ship reaches. Unknown objects create additional risks. A faint red dwarf may be difficult to detect at great distance. A white dwarf, neutron star, or isolated black hole may emit little visible light. An isolated stellar mass black hole would be especially difficult to see directly, because it produces no light of its own. It could reveal itself by gravitationally bending the light of background stars or by affecting nearby matter. If the spacecraft fails to detect such an object, its trajectory may be altered unexpectedly. The chance of passing extremely close to an unseen compact object is low because space is vast. A successful navigation model must still account for uncertainty in the mass distribution along the route. Dense regions of the galaxy are more difficult than sparse ones. Near the galactic centre, stars are more crowded, gravitational encounters are more frequent, and the field changes more rapidly across distance. A traveller hoping to simplify navigation might avoid such regions, even if the direct route passes through them. The shortest geometric path may not be the safest or easiest physical path. Gas clouds can also matter, although their gravity is usually spread across a large volume. Massive molecular clouds contain enough material to influence nearby stars and spacecraft. They may obscure the background sky and make stellar navigation harder at the same time. The traveller must therefore map both visible landmarks and invisible gravitational sources. One method would be to observe gravitational lensing. General relativity predicts that mass bends the path of light. When light from a distant star or galaxy passes near a massive object, the light follows the curved geometry around that mass. The background source may appear shifted, distorted, brightened, or multiplied into several images. This effect allows astronomers to detect matter that may not be visible directly. A lost spacecraft could monitor the apparent positions of distant stars and quasars. If one object shifts in a way that cannot be explained by the spacecraft's motion, an intervening mass may be bending the light. Microlensing occurs when a compact foreground object passes close to the line of sight toward a background star. The background star temporarily brightens in a characteristic way. An isolated dark object may therefore announce itself by changing the light of something behind it. This is useful for mapping hidden masses, but it introduces another navigation complication. The apparent position of a reference star may not be its undisturbed direction. Gravity along the line of sight can bend the incoming light. A traveller may aim according to the observed position and unknowingly use a distorted landmark. Most gravitational lensing effects from ordinary stars are tiny, unless the alignment is close. Precision navigation across light years is sensitive to tiny effects. The system must distinguish a real change in the star's position from an apparent shift caused by lensing. The same mass can therefore affect navigation twice. It pulls on the spacecraft and bends the light used to determine where the spacecraft is. Near very massive objects, the effects become stronger. A black hole curves space-time so severely that beyond the event horizon, no light can escape. Outside that boundary, objects and light can orbit, fall, or pass by on strongly curved trajectories. A spacecraft would normally avoid such a region. It could not treat the surrounding space as a flat background with a small correction added afterward. Time itself also behaves differently in strong gravity. Clocks closer to a massive object run more slowly relative to clocks farther away. This gravitational time dilation must be included when comparing signals and predicting motion. The effect is measurable even around Earth. Clocks at different altitudes tick at slightly different rates. Satellite navigation systems account for this because ignoring it would cause position errors to accumulate. In deep space, a traveller passing near a neutron star or black hole could experience much larger timing differences. The ship's onboard clock remains normal to the crew. Every local second feels like a second. A distant observer may calculate a different amount of elapsed time. If the navigation system compares its clock with signals from far away, it must correct for the gravitational environment along the route. A timing error then becomes another trajectory error. The computer may predict the sun's future position using the wrong elapsed time. It may command a maneuver too early or too late. The ship may cross the correct path after the solar system has already moved away from the meeting point. Newtonian gravity can describe most stellar navigation when speeds are low compared with light, and gravitational fields are not extreme. General relativity becomes necessary when higher precision, stronger fields or high velocities are involved. The two descriptions use different language. In Newton's picture, gravity is a force pulling objects away from the straight paths they would otherwise follow. In general relativity, a freely moving object follows the straightest possible path through curved space-time. This path is called a geodesic. The spacecraft is not being pulled away from a straight route in the ordinary sense. The geometry that defines the route is itself curved by mass and energy. A useful comparison can be made with motion across Earth's surface. Two travellers begin at the equator, walking north along lines that initially seem parallel. As they approach the North Pole, their paths move closer together. Neither traveller turned sideways, each followed the straightest available route across the curved surface. The convergence happens because the surface is curved. Space-time curvature is more complicated because it includes time as well as 3 spatial dimensions, but the general lesson is similar. What counts as a straight path depends on the geometry. A flat map can misrepresent a route across a curved planet. A flat spatial diagram can also misrepresent motion through a gravitational field. The navigation computer must use the correct geometry. Around the Sun, the curvature is mild enough that Newtonian orbital mechanics gives extremely accurate results for many missions. For the orbit of Mercury and for precise timing, relativistic corrections become noticeable. Across the galaxy, most local fields are weak, but the journey may be so long that small corrections matter. The ship also cannot calculate its trajectory using only the masses as they appear now. It observes distant objects through delayed light. A star 100 light-years away is seen where it was when the light began its journey. The traveller must estimate where the star is currently located before calculating its present gravitational influence. Gravity itself does not provide instantaneous information in relativity. Changes in the gravitational field propagate at the speed of light. If a distant star moves, explodes, or interacts with another object, the spacecraft does not immediately respond to knowledge of the new arrangement. The changing gravitational influence reaches the traveller according to the causal structure of space-time. For most smooth stellar motion, astronomers can predict the current configuration from earlier observations. Sudden events or poorly known systems add uncertainty. The traveller is therefore calculating a path through a gravitational field that must be reconstructed from old light. A visible star shows its previous position. Its spectrum gives previous motion. The model advances that information forward. The calculated mass distribution then predicts the ship's future acceleration. Every stage contains assumptions. When the spacecraft later compares the predicted sky with the observed one, a disagreement could have several causes. Its position may be wrong. Its velocity may be wrong. The star's motion may have been miscalculated. An unseen mass may be bending the light. The gravitational model may be incomplete. One error can imitate another. Repeated observations help separate them, but the process becomes demanding across long distances. The spacecraft may need years of measurements to determine whether a tiny apparent drift comes from its own acceleration or the proper motion of a reference object. During those years, gravity continues changing the route. A lost traveller cannot eliminate this problem by stopping because there is no universal stop. The ship can reduce its velocity relative to one frame, but it remains inside the galactic field. It continues falling through the Milky Way along some path. It could try to enter orbit around a known star while rebuilding the map. That would create a stable local reference and provide time for observation. Entering orbit requires detecting the star, approaching it with the correct velocity, and performing enough braking to become gravitationally bound. Without sufficient propulsion, the spacecraft may simply pass through the system and continue onward. A highly advanced traveller might use a star's light, magnetic field, stellar wind, or gravity to adjust the trajectory. Each method depends on accurate approach conditions. Gravity is useful because it is available everywhere, but it does not follow instructions. It curves the actual path determined by mass, velocity, and geometry, not the path the crew intended to take. Reaching the solar system therefore requires a model that is continually corrected. The traveller predicts the gravitational field, calculates a geodesic or an approximate orbital trajectory, measures deviations, and updates the route. No single line drawn at the beginning can remain trustworthy forever. Even after the spacecraft enters the correct region of the Milky Way, the Sun's gravity begins reshaping the approach. The ship may arrive with a large velocity relative to the solar system. It must convert an interstellar trajectory into a solar orbit or perform enough braking to avoid passing straight through. Aiming directly at the Sun would allow its gravity to accelerate the spacecraft inward. That acceleration does not help the vehicle stop. Unless energy is removed, the ship speeds up as it falls toward the Sun and slows again as it climbs away, leaving with a speed related to the one it had on arrival. Gravity can turn the path without automatically capturing the spacecraft. To become bound to the Sun, the ship must lose energy. It can fire engines, interact with a planet, use drag if suitable material is present, or employ another physical mechanism. A traveller who reaches home with no braking capability may see the solar system briefly and then leave it again. Finding the correct place is only part of the task. Matching the motion of that place matters just as much. The calculation becomes still more complicated when the ship travels at relativistic speed. Distances and elapsed times no longer transform according to ordinary Newtonian rules. Observers moving relative to one another disagree about simultaneity, and gravity affects both clocks and the geometry used to define the route. At that point, the map is not merely curved by matter. Its measurements depend on the observer carrying it, which means the next problem is deciding how Earth's coordinates, the spacecraft's coordinates, and the incoming signals can all be translated between frames that do not share the same space or the same time. At ordinary speeds, this sounds more troublesome than it usually is. A person walking through a train can describe their motion relative to the carriage, while someone standing beside the track describes the same person relative to the ground. The two observers obtain different speeds, but the relationship between their measurements is simple. Add the speed of the train in one direction, subtract it in the other, and the descriptions fit together. This everyday method works because all the speeds involved are extremely small compared with the speed of light. Once a spacecraft begins moving at a significant fraction of light speed, the simple method fails. Space and time no longer behave as separate quantities that every observer measures in the same way. Distances, durations, and simultaneity depend on the observer's state of motion. The events themselves remain real. If two spacecraft collide, every observer agrees that the collision occurred. If a radio signal is emitted and later received, everyone agrees that the emission can influence the reception. What changes is the coordinate description assigned to those events. One observer may calculate a long distance and a short duration. Another may calculate a shorter distance and a longer duration. both can be correct within their own reference frames. This is not a matter of faulty clocks or bent rulers, it is how space-time is structured. The result begins with the speed of light. Every inertial observer measures the same value for light travelling through a vacuum, regardless of the observer's own constant velocity. Imagine two spacecraft moving apart. One switches on a lamp. The crew on that ship measures the light moving away at the usual speed. The crew on the other spacecraft also measures that same speed, even though they are moving relative to the source. They do not measure the speed of light plus or minus the speed of the spacecraft in the ordinary way. To preserve this agreement, their measurements of distance and time must differ. A second on one ship is not necessarily equal to a second assigned to the same distance sequence by the other ship. A measured length along the direction of travel is not necessarily the same in both frames. Events judged simultaneous in one frame may occur at different times in another. These effects are described by special relativity. Time dilation is one of the best-known consequences. A moving clock is measured to tick more slowly relative to an observer who considers it to be moving. Suppose Earth sends a spacecraft toward a distant star at a very high speed. People on Earth watch the spacecraft's clock through signals and calculate that it is running slowly. The crew on the spacecraft considers its own clock normal. Their heartbeats, conversations, instruments, and cups of tea all proceed at the usual rate. They do not feel time slowing. From their perspective, Earth is moving away, and clocks on Earth appear to run slowly. This may sound contradictory, but the situations remain symmetrical only while the observers remain in constant relative motion and do not reunite. When the spacecraft turns around and returns, acceleration changes the relationship between the frames. The traveller on Earth can then compare clocks directly, and the traveller may have experienced less elapsed time. This is the idea behind the twin scenario. One twin travels at high speed and returns younger than the twin who remained on Earth. The effect is not limited to imaginary voyages. Fast-moving particles survive longer in laboratories because of time dilation. Precise clocks carried on aircraft and satellites accumulate different amounts of time from clocks remaining on Earth. At interstellar speeds, the differences can become large enough to shape the entire navigation problem. The traveller may experience 10 years while much more time passes on Earth. The ship's onboard calendar says one date. Earth's predicted calendar says another. Neither calendar is malfunctioning. They measure elapsed time along different paths through space-time. This elapsed time carried by an object is often called proper time. It is the time measured by a clock travelling with that object. The spacecraft follows one world line, Earth follows another. The amount of proper time accumulated along each can differ when the paths involve different velocities and gravitational conditions. For navigation, the traveller must know which time appears in every part of the stored data. A star catalogue may list positions for a particular Earth-based date. A pulsar model may predict pulse arrival times in a frame connected to the solar system. The spacecraft's engine log uses onboard proper time. A message from Earth includes the time at which it was transmitted according to clocks near Earth. Those values cannot always be compared directly. The navigation computer must transform them into a common framework. If it treats the ship's elapsed time as though it were identical to Earth's elapsed time, the predicted location of the solar system will be wrong. The error may amount to days, years, or much more, depending on the speed and duration of the journey. During one Earth year, the planet completes an orbit around the Sun. During a few 100 million Earth years, the Sun completes an orbit around the Milky Way. A timing disagreement that seems like a bookkeeping problem becomes a large spatial disagreement because the destination continues moving. Length contraction creates another difference. An observer measures an object moving relative to them as shortened along the direction of motion. For the traveller, the distance to the destination may be shorter than the distance measured in Earth's frame. This is one reason a traveller moving near light speed could cross a large interstellar distance within a much shorter personal time than Earth-based observers calculate. The galaxy does not physically compress around the ship in a way the crew can touch. The measured distance between simultaneous positions depends on how simultaneity is defined in that frame. That last point is important, because measuring the length of a moving object requires recording the positions of both ends at the same time. If observers disagree about which distant events are simultaneous, they can disagree about the measured length without contradiction. A map is built from positions assigned at chosen times. Once simultaneity becomes frame-dependent, a map of moving objects becomes frame-dependent as well. Consider a map showing the locations of the Sun, several stars, and the spacecraft at one moment. In Earth's frame, the map includes the positions of all those objects at the same Earth frame time. The traveller's frame divides space-time into present moments differently. The traveller's map may assign different positions to those moving objects, because the phrase "at the same time" selects a different set of events. There is no universal snapshot of the galaxy that every observer must accept as the current one. This does not mean astronomers cannot make maps. They choose a frame, define a time coordinate, and state the convention. The map then becomes precise. Trouble begins when information created in one frame is used as though it belonged to another. A lost traveller may open a stored map and see the Sun marked at a particular galactic coordinate. That coordinate was calculated for a specified time in a specified frame. The spacecraft is now moving rapidly relative to that frame. The computer must transform the map before using it. At low speeds, the correction might be small enough to ignore. At relativistic speed, ignoring it could send the spacecraft toward a place that does not correspond to the desired future encounter. Relativity also changes the appearance of the sky. A moving observer does not see incoming light arriving from exactly the same directions as an observer at rest relative to the source frame. The apparent shift is called relativistic aberration. At modest speeds, the effect is small. Earth's orbital motion produces a measurable annual aberration in star positions. Astronomers correct for it when making precise observations. At speeds close to that of light, the effect becomes severe. Light from a wide region ahead appears concentrated toward the direction of travel. Stars that would ordinarily cover much of the forward sky crowd into a smaller angular area. The view behind also changes. The traveller does not see the calm, evenly distributed star field recorded in an Earth-based catalogue. The sky appears rearranged by motion. A star tracker designed for ordinary velocities could fail because the expected angular separations no longer match. The hardware may be functioning perfectly, while the software concludes that no known pattern exists. To recover orientation, the system must estimate the velocity and mathematically reverse the aberration. Yet the apparent stellar pattern may be one of the main sources used to estimate that velocity. The navigation problem again becomes a process of testing possible solutions. The computer assumes a velocity, corrects the observed sky, compares it with the catalogue, and adjusts the assumption until the patterns agree. Frequency shifts provide additional information. Light from sources ahead is shifted toward higher frequencies when the spacecraft moves toward them. Light from behind is shifted toward lower frequencies. This relativistic Doppler effect can move radiation into or out of the visible range. A red star ahead might appear bluer. Infrared radiation may shift into visible light. Visible light may shift into ultraviolet. Behind the ship, visible stars may move toward infrared wavelengths and become difficult to see with ordinary cameras. The crew's view depends on the detectors available. A navigation system using several parts of the electromagnetic spectrum can track these shifts. It can compare known spectral lines with their observed frequencies and estimate relative motion. At very high speed, the changes are not decorative. They affect detection, instrument design, and safety. Radiation ahead becomes more energetic. The cosmic microwave background, normally detected as faint microwave radiation, shifts toward higher frequencies in the forward direction. The spacecraft may encounter a concentrated field of energetic photons. Interstellar gas and dust also strike with much greater energy at relativistic speed. A particle that would be harmless during slow travel can become a serious hazard. Navigation sensors must continue operating in an environment altered by the spacecraft's own motion. Brightness changes as well. Relativistic beaming can make radiation ahead appear more intense, and radiation behind appear weaker. A star's apparent brightness is therefore not determined only by its luminosity and distance. The spacecraft's velocity contributes. If the navigation computer estimates distance from brightness without applying the correct relativistic correction, it may place the star at the wrong range. That wrong range affects parallax predictions and the reconstructed position of the ship. Direction, frequency, brightness, distance, and velocity become linked. A single observation cannot be interpreted safely without a model of the frame in which it was made. Radio communication creates another set of complications. Suppose Earth transmits a navigation update toward the spacecraft. The message travels at light speed. If the ship is moving away, the signal takes longer to catch it. If the ship is moving toward Earth, the distance closes while the message travels. The signal arrives, Doppler shifted, and the intervals between transmitted pulses may not match the intervals measured by the receiver. The ship must determine when the message was sent, how the transmitter was moving, how the ship was moving, and which time standard was used. A sentence such as "Earth is at these coordinates now" would be almost useless without those details. By the time the message reaches the spacecraft, Earth has moved. The spacecraft has moved. The meaning of now depends on the frame. A useful message would instead include the transmission event, the coordinate frame, the time standard, the estimated ephemeris, and enough information for the receiver to propagate the positions forward. Modern deep space communication already relies on careful timing and frame definitions. Signals exchanged with planetary probes are corrected for the motion of Earth, the spacecraft, and the intervening geometry. Interstellar distances increase the delay from minutes or hours to years or centuries. There can be no ordinary conversation. A traveller 100 light-years away sends a request for directions. Earth receives it 100 years later. The response then requires another 100 years to return. By the time the traveller receives the answer, 200 years have passed in Earth's frame since the request was transmitted. The ship has continued moving throughout that period. The response describes a situation that must be projected forward again. If the spacecraft is moving relativistically, the amount of onboard time that passed may be very different. The crew may receive what feels like a delayed answer from a much older Earth. The message remains useful only if the navigation system understands the relationship between the frames. Clock synchronization becomes particularly difficult across distance. On Earth, two nearby clocks can be placed together, synchronized, and separated. For distant clocks, signals are exchanged and travel time is accounted for. Relativity shows that synchronization depends on the frame. Two clocks judged, synchronized in one inertial frame, may not be synchronized in another moving frame. This is connected to the relativity of simultaneity. A spacecraft cannot simply assume that an Earth clock and an onboard clock share a universal present. It needs a defined procedure for comparing them. One common method uses light signals. An observer sends a signal to a distant clock, receives a reply, and assumes the travel time is divided symmetrically between the outgoing and returning paths. That procedure defines synchronization within the observer's frame. A different moving observer applies the same rule and obtains a different set of synchronized clocks. Neither has uncovered a hidden universal time. For a navigation computer, this is manageable because the transformations are known. The real danger is forgetting which synchronization convention was used by stored data. An old catalogue may reference a barycentric coordinate time associated with the solar system. Engineering records may use terrestrial time or another standard. The spacecraft's local clock measures proper time affected by its motion and gravitational history. The software must preserve the labels. Removing a label because two time values look similar is a very efficient way to become lost. General relativity adds gravitational time dilation. Clocks in stronger gravitational fields tick more slowly relative to clocks in weaker fields. A clock near the surface of Earth differs from one high above the planet. A clock near the Sun differs from one in interstellar space. A clock passing close to a neutron star or black hole can accumulate substantially less time than a distant clock. The traveller's route therefore matters even if the departure and arrival speeds are the same. Two spacecraft can leave the same point, follow different paths through gravity, and reunite with different elapsed times on their clocks. The navigation system needs a record of the entire trajectory, not only the current velocity. GPS provides a familiar example of the practical need for relativistic correction. Satellites move rapidly relative to clocks on Earth, producing special relativistic time dilation. They are also higher in Earth's gravitational field, producing a general relativistic effect in the opposite direction. The combined difference must be corrected. Without those corrections, calculated positions would drift noticeably. Finding a street on Earth already requires clocks that respect relativity. Finding Earth from deep space requires the same principles across a far larger distance and a much longer duration. The traveller could maintain several time values. One clock records onboard proper time. The computer also calculates coordinate times for selected reference frames. Incoming messages are converted according to the frame and gravitational conditions of the sender. This is mathematically possible, but it depends on knowing the ship's trajectory well enough to calculate the transformations. If the trajectory is uncertain, the relationship between the clocks is uncertain too. Timing error and position error reinforce each other. The spacecraft needs accurate time to determine position from signal arrival. It needs accurate position and velocity to correct the time. Repeated measurements can reduce the uncertainty. Signals from multiple sources help because each follows a different path and arrives from a different direction. Pulses may act as natural clocks. Their regular pulses allow a spacecraft to compare observed arrival times with predictions. Several pulses distributed across the sky could help determine both position and time. Their signals are not perfect clock ticks. Pulsars gradually slow, occasionally change their rotation in sudden events called glitches, and move through space. Radiation also passes through interstellar material, which can delay different frequencies by different amounts. Accurate pulsar navigation requires updated timing models. A traveller carrying an ancient model may find that the pulses no longer arrive according to prediction. The mismatch could reveal how much time has passed, but only if the correct pulsars have been identified and their long-term behaviour can be reconstructed. Distant quasars provide stable directions, while pulsars provide timing patterns. Stars provide local structure. Together, these references can help build a relativistic map. The map remains observer-dependent. Its usefulness comes from specifying the observer and providing the transformations, not from eliminating relativity. There is one quantity on which observers do agree: the space-time interval between events. Different observers divide that interval into different amounts of space and time, but the combined quantity remains invariant. This invariant structure is what allows their maps to be translated consistently. Relativity does not say that every description is equally disconnected from every other. It gives exact rules relating valid descriptions. For the traveller, that is reassuring. Earth's map and the ship's map can be reconciled if enough information survives. The spacecraft must know its velocity relative to the chosen frame. It must know the gravitational fields that affected its clocks. It must understand how the stored coordinates were defined. It must correct the observed sky for aberration and Doppler shifts. It must advance delayed signals to the appropriate future position. After all of that, the ship can calculate an intercept event. Relativity can translate the map between observers, but it cannot make the destination stop moving. The solar system does not remain at a fixed point while the rest of the Milky Way moves around it. The Sun, Earth, the other planets, and the smaller objects bound to the Sun are all travelling through the galaxy together. A traveller trying to return home must therefore locate a moving system, predict its future path, and arrive with a velocity that allows the spacecraft to remain nearby. Earth's movement around the Sun is only the first layer. The planet travels along its orbit at about 30 kilometers per second. The Sun, carrying the planets with it, moves around the center of the Milky Way at roughly 230 kilometers per second, although the precise value depends on how the galactic motion is measured and modeled. At that speed, the solar system travels billions of kilometers during an ordinary Earth year. The distance sounds enormous, but the Milky Way is much larger. The Sun is located roughly 26,000 light-years from the galactic center, and one complete orbit takes approximately 230 million years. Estimates vary because the galaxy does not have a perfectly simple mass distribution, and the Sun's path is not an exact circle. One orbit of the Sun around the Milky Way is sometimes called a galactic year. Earth is about 4.5 billion years old, so the solar system has completed only around 20 galactic orbits during the planet's entire history. Dinosaurs lived on Earth during a different portion of the Sun's galactic path. The first humans appeared during a very small fraction of the current orbit. For navigation, this means that an ancient coordinate for the solar system cannot simply be reused. The Sun may have travelled thousands of light years since the coordinate was recorded. Even over much shorter periods, the displacement becomes important. During 1,000 years, the Sun moves a substantial fraction of a light year along its galactic orbit. During 1 million years, it travels hundreds of light years. A spacecraft returning after a long journey cannot aim for the location from which it originally departed. That point has been left behind. The traveller needs to calculate where the Sun is now and where it will be when the spacecraft arrives. This calculation is more complicated than moving a marker around a circular track. The Milky Way does not rotate as a solid disk. Stars at different distances from the galactic center have different motions, and the distribution of mass throughout the galaxy affects their orbits. The Sun follows the gravitational field produced by stars, gas, dust, the central regions of the galaxy, and the much larger distribution of dark matter. Its orbit is approximately circular, but only approximately. The Sun can move inward and outward relative to its average distance from the galactic center. It also moves above and below the main plane of the galactic disk. The full path is therefore a three-dimensional orbit with smaller oscillations added to the larger motion around the galaxy. A simple map showing the Sun moving along one neat circle is useful for an introduction. A navigation system needs a better model. Nearby stars also influence the local motion. Most stellar encounters occur at large enough distances that their effects are modest. Over millions of years, however, stars pass through the Sun's broader neighbourhood and slightly alter the gravitational conditions. A close stellar passage can disturb distant comets in the outer solar system. It may also change the Sun's motion by a small amount. The Sun is massive compared with planets, but it is not isolated. It participates in the changing gravitational environment of the galaxy. A traveller with an old galactic map would need to update the positions and velocities of many stars before predicting the solar system's path accurately. If nearby stars have moved differently from the stored model, the calculated location of the Sun will drift from its real one. The traveller might know the average galactic orbit very well, and still miss the current stellar neighbourhood. The situation resembles predicting the location of a boat carried by a broad ocean current. Knowing the average direction of the current is useful. It does not account for every smaller flow, turn, and disturbance experienced by the boat. The Milky Way carries the solar system around the galactic center, but the solar system also has its own motion relative to nearby stars. Astronomers sometimes describe a local standard of rest, which represents the average motion of material near the Sun as it orbits the galaxy. The Sun does not remain perfectly at rest relative to this local average. It has a peculiar velocity, meaning an additional motion relative to the chosen standard. The word peculiar does not mean the Sun is behaving suspiciously. It is the technical term for motion that differs from the average flow. Every nearby star has its own peculiar motion. Some travel through the local region more quickly than others. Some move inward or outward through the galaxy. Some have orbits tilted relative to the main disk. The local stellar neighbourhood is therefore constantly changing. A traveller cannot search for the Sun by looking for a permanent arrangement of neighbouring stars. The arrangement that existed at departure may have spread apart or been replaced. The farther the traveller moves through time, the less reliable the old neighbourhood becomes. A map could predict these changes if it contained accurate positions and velocities for all relevant stars. In practice, every measurement includes uncertainty. Advance those uncertain motions over 1,000,000 years, and the predicted locations become broad regions rather than exact points. The traveller may be able to determine where the Sun is likely to be, without knowing its precise location. That distinction is important because a likely region can still be several light years across. The traveller could narrow the search by identifying the Sun's spectrum and measuring the properties of nearby systems. The planets might produce small changes in the Sun's motion, and advanced instruments could search for those gravitational effects. Artificial signals from Earth could help, assuming Earth is still transmitting signals that can be detected at the traveller's distance. The route remains difficult because the traveller is not the only object moving through the Milky Way. The spacecraft also has a galactic orbit. If it is located far from the solar system, its velocity may differ greatly from the Sun's. Pointing toward the Sun and accelerating in that direction does not erase the sideways motion already carried by the ship. Both objects are falling through the galaxy, but they may follow different paths. The spacecraft must alter its own galactic trajectory until it intersects the future trajectory of the Sun. This is an orbital interception problem on a galactic scale. A direct geometric line may not be an efficient route. The spacecraft may need to change speed relative to the galactic centre, adjust its motion above or below the disk, and compensate for the gravitational field encountered along the way. When it finally reaches the Sun's region, it must also match the motion of the solar system. A vehicle passing through the correct position at several hundred kilometers per second relative to the Sun has technically found home, but only briefly. Without enough braking capability, it continues past. The Sun's gravity bends the trajectory, but gravity alone does not guarantee capture. The spacecraft must lose enough energy relative to the solar system to remain gravitationally bound. It could fire engines, interact with a planet, use a carefully planned close solar pass combined with propulsion, or employ some other method of reducing velocity. The important point is that position and velocity must both match. Finding the place where the solar system has moved is not enough if the ship arrives with the motion of a completely different galactic orbit. There is also a larger motion involving the Milky Way itself. Our galaxy is part of the Local Group, a collection containing the Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and many smaller galaxies. The Milky Way moves relative to the other members of this group. The Local Group also moves relative to larger structures of galaxies. No galaxy serves as a fixed background. At first, this might seem to make navigation hopeless. If the Sun moves through the Milky Way moves through the Local Group, and the Local Group moves relative to more distant galaxies. Perhaps every target is being carried away by a series of larger motions. That description is useful only if each motion is tied to a stated reference frame. The Milky Way does not need to have one absolute velocity. It can have different velocities relative to Andromeda, the cosmic microwave background, distant galaxy clusters, or any other chosen reference. A traveller returning from another part of the Milky Way mainly needs the solar system's position relative to the galaxy. A traveller returning from another galaxy must also model the motion of the Milky Way relative to the intergalactic environment. On sufficiently large scales, another physical effect becomes important. The universe is expanding. This does not mean galaxies are flying outward from one central explosion point into pre-existing empty space. There is no known central location from which the expansion began. The distances between widely separated unbound galaxies increase because the large-scale geometry of space changes over time. A common comparison uses dots drawn on the surface of an inflating balloon. As the balloon expands, every dot sees the other distant dots moving away. No dot on the two-dimensional surface is the centre of the expansion within that surface. The comparison is limited. The universe is not known to be the surface of a balloon expanding into an external room. The useful part is that the distance between points can increase without requiring one special point to be the centre. On large scales, distant galaxies generally recede from one another. The relationship is described by the Hubble-Lemaitre law. The farther away a galaxy is, the greater its average recession speed due to cosmic expansion. The recession speed is approximately equal to the Hubble parameter multiplied by distance. Near the present time, the value of the Hubble parameter is around 70 km per second for each megaparsec of distance, although different measurement methods give somewhat different results. A megaparsec is about 3.26 million light-years. This means that a galaxy 1 megaparsec away participates in the average expansion at roughly 70 km per second. A galaxy 10 megaparsecs away participates at roughly 700 km per second. Real galaxies also have peculiar velocities caused by local gravity. The measured motion is a combination of cosmic expansion and movement through the local gravitational environment. This distinction prevents a common misunderstanding. The Hubble flow does not pull apart every object. Earth is not expanding. The solar system is not expanding. The distance between the Sun and Earth does not increase according to the Hubble-Lemaitre law. The Milky Way itself is not being stretched apart by cosmic expansion. These systems are gravitationally bound. Their internal gravity, along with electromagnetic and nuclear forces at smaller scales, is strong enough to maintain their structure. Cosmic expansion becomes dominant across much larger distances, where matter is not bound into the same local system. Even the local group does not simply follow the general expansion internally. The Milky Way and Andromeda are moving toward one another because their mutual gravity overcomes the local Hubble expansion. They are expected to interact and merge on a timescale of several billion years. This does not contradict the expansion of the universe. Local gravitational motion can oppose the average large-scale flow. Cars can move toward one another on a road, even while the road network as a whole is being extended. For a traveller within the Milky Way, cosmic expansion has almost no practical effect on the route home. Galactic gravity dominates. For a traveller located in another gravitationally bound part of the local group, local motion remains more important than the general Hubble flow. Once the traveller is separated from the Milky Way by millions or billions of light-years, cosmic expansion becomes part of the navigation problem. The distance to home may increase while the spacecraft travels. This does not mean the spacecraft experiences a local force pushing it backward. In a sufficiently empty region, it follows a path through expanding space-time. The relationship between distant locations changes as the overall scale of the universe changes. A simple calculation using speed multiplied by time is no longer enough across cosmological distances. The traveller must use a model of the universe's expansion history. The expansion rate has not remained constant throughout cosmic history. The early universe evolved through periods dominated by radiation and matter. At later times, the expansion began accelerating, which is usually attributed to dark energy in the standard cosmological model. Dark energy is the name given to whatever is responsible for this accelerated expansion. Its underlying nature is still not fully understood. The effect matters because a traveller trying to return from a very distant galaxy may be chasing a destination whose proper distance is increasing. Light itself is affected. As light travels through expanding space, its wavelength is stretched. This produces cosmological redshift. Light emitted by a distant galaxy arrives with a longer wavelength than when it began. The amount of redshift helps astronomers estimate how much the universe expanded during the light's journey. A lost traveller could use redshifts to study the large-scale distribution and motion of galaxies. Yet redshift alone does not provide a simple current distance. Part of the measured redshift may come from peculiar motion. The relationship between redshift distance and travel time depends on the cosmological model. The The traveller also sees distant galaxies in the past because their light has taken millions or billions of years to arrive. The observed position of the Milky Way, if it could be seen from an enormous distance, would be the position and appearance it had when the detected light was emitted. The galaxy continues moving and evolving during the light's journey. Across intergalactic distances, the traveller must combine light travel delay, cosmic expansion, local galactic motion, and the spacecraft's own movement. The visible direction of home is not automatically the direction of a successful route. Suppose the traveller is 1 billion light-years away and observes the Milky Way using light that left roughly 1 billion years earlier. The traveller is seeing an older version of the galaxy. During that time, the Milky Way has moved relative to surrounding structures, the Sun has completed several galactic orbits, and the universe has expanded. A route aimed at the observed image would target where the old light says the galaxy was, not necessarily where an interception can occur. The navigation system must reconstruct the Milky Way's world line through an expanding universe. On very large scales, the word distance itself requires care. Cosmologists use several definitions because different measurements answer different questions. There is the distance light has travelled. There is the present proper distance between locations. There is a distance inferred from the apparent brightness of an object. There is another inferred from its apparent angular size. These values are related, but they are not always identical. A traveller who says that home is 10 billion light-years away must specify which cosmological distance is meant. Using the wrong definition could produce a severely incorrect travel estimate. Recession speeds can also exceed the speed of light at sufficiently large distances. This does not violate special relativity because the galaxies are not locally moving through space past nearby observers faster than light. The large distance between regions increases because space expands. Special relativity forbids an object from locally passing another object faster than light. General relativity allows the proper distance between very distant unbound regions to increase at a rate greater than light speed. This is another reason ordinary velocity addition cannot be used for cosmological navigation. A spacecraft cannot simply accelerate until it exceeds the recession speed in a local sense. It remains limited to speeds below light relative to nearby matter. Whether it can reach a distant target depends on the entire future expansion of space. Some regions currently visible to us are already so distant that a signal sent from Earth today may never reach them, if accelerated expansion continues as expected. We see them because their old light began travelling toward us when they were closer in the relevant cosmological sense. Visibility does not guarantee future reachability. There is a cosmological event horizon beyond which events occurring now can never send signals that reach us, assuming the standard model of continued accelerated expansion. A traveller beyond the corresponding boundary could see old light from the Milky Way and still be unable to return or send a new message that ever arrives here. Home would remain visible as a historical image while being physically unreachable through any future path limited by the speed of light. That is a very different kind of being lost. Within the Milky Way, the main challenge is identifying and intercepting a moving target. Across extreme cosmological distances, space-time itself may prevent the interception. No engine can overcome a causal horizon by providing more ordinary thrust. The exact location of the cosmological horizon depends on the expansion history and the nature of dark energy. If dark energy changes over time, the long-term result could differ from the simplest prediction. Under the usual model, however, more distant galaxies gradually pass beyond practical communication. Their light becomes increasingly redshifted and faint. Far in the future, observers in the Milky Way's descendant galaxy may see little evidence of galaxies outside the gravitationally bound local remnant. The large-scale universe will become more difficult to map because much of it will no longer be observable. A traveller equipped with an old map might search for galaxies that have faded beyond detection. The structures used as distant reference points would no longer be visible. Closer galaxies remain measurable for much longer, and objects within the local gravitationally bound region stay together. The Hubble flow does not slowly carry Earth away from the Sun or pull the planets apart. It changes the relationship between the Milky Way and sufficiently distant unbound galaxies. For the journey home, the scale of the traveller's displacement determines which physics dominates. A few light years away, stellar motion and measurement error are central. Thousands of light years away, the Sun's galactic orbit and the changing structure of the Milky Way become critical. Millions of light years away, the motion of galaxies within the local group must be included. Hundreds of millions or billions of light years away, cosmic expansion changes the route, the signal delay, the definition of distance, and possibly whether return remains physically possible. In every case, the original address of Earth becomes outdated. Earth moves around the Sun moves around the Milky Way moves within the local group. Distant galaxies participate in the changing large-scale geometry of the universe. The traveller does not need an old location. The traveller needs the future event at which the spacecraft can meet the moving solar system. Calculating that event requires information about motions that cannot be observed instantly. Even before cosmic expansion makes a region unreachable, light travel time can make the visible map badly outdated, because the Earth the traveller sees is always the Earth that existed when the light began its journey, not the Earth that must be found when the spacecraft finally returns. Light is fast enough to cross the distance from Earth to the Moon in a little more than 1 second. It reaches the Sun in roughly 8 minutes. Those delays are small in everyday life, but they establish the rule that applies everywhere else. Information never arrives instantly. Every photograph, radar echo, radio message and telescope image describes an earlier state of the source. When you look at the Moon, you see it slightly more than a second in the past. When you look at the Sun, you see it as it was about 8 minutes earlier. Jupiter may appear tens of minutes out of date, depending on where Earth and Jupiter are in their orbits. The nearest other star system is seen more than 4 years in the past. A traveller 100 light-years from Earth receives light that left the solar system 100 years earlier. At 1,000 light-years, the delay becomes 1,000 years. From the far side of the Milky Way, the image could be tens of thousands of years old. The traveller is not looking through a live window. The traveller is receiving an archive. That archive may still be useful. Old information can be advanced forward with a model. If the position and velocity of the Sun were known at the time the light was emitted, the navigation computer could estimate where the solar system moved during the delay. The estimate must include the Sun's galactic orbit, the motion of nearby stars, the gravitational field of the Milky Way, and any later corrections learned from other observations. The farther away the traveller is, the longer the extrapolation, and the more opportunity there is for small uncertainties to grow. Seeing Earth directly would be much harder than simply looking toward the Sun. Earth is small, faint, and usually lost in the glare of its star. From a large distance, the solar system would appear as a single point unless the telescope had an enormous effective aperture and exceptional control over scattered light. The angular separation between Earth and the Sun decreases with distance. 1 astronomical unit is a large distance inside the solar system, but it becomes a tiny angle when viewed from another star. From 10 parsecs away, the maximum separation is only a fraction of an arcsecond. An advanced instrument might still detect Earth indirectly. It could observe the slight dimming produced when the planet crosses the face of the Sun. It could measure the Sun's small motion around the solar system's barycenter. It might separate the planet's reflected light from the star and study the spectrum. None of these methods gives a continuously updated location. A transit occurs only when the orbit is aligned correctly with the observer. The stellar wobble must be measured across time. Reflected light still carries the same travel delay as every other signal. If the traveller sees Earth completing an orbit, that orbit happened years, centuries, or millennia earlier. A familiar image can therefore be dangerously persuasive. The planet may appear at a particular point beside the Sun, and the navigation display may place a marker there. By the time the detected photons reach the spacecraft, Earth has completed many later orbits. For a traveller 4 light-years away, Earth moves around the Sun 4 times between emitting the observed light and the arrival of that light. If the traveller immediately begins a return journey that takes another 4 years in the solar system's frame, Earth completes roughly 4 more orbits. The image used for aiming is about 8 orbital cycles removed from the encounter. The simple response is to predict the orbit. Earth's year is regular enough that a good ephemeris can place the planet far more accurately than direct viewing from several light-years away. Yet the prediction requires the correct time, and the spacecraft must know how its own clock relates to the time standard used by the ephemeris. A timing mistake shifts the predicted orbital phase. 1 day of error places Earth millions of kilometers away from the expected point. 1 hour still represents more than 100,000 kilometers of orbital travel. The situation becomes more demanding when the spacecraft's speed is relativistic. The crew's elapsed time may differ from the time accumulated on Earth. Incoming light is Doppler shifted, aberrated and changed in apparent brightness. The navigation computer must correct the observation before comparing it with an Earth-based model. A signal from behind the spacecraft may be red-shifted if the ship is moving away from Earth. The interval between pulses becomes longer. If the spacecraft turns and moves toward home, the signals can become blue-shifted and arrive more rapidly. The ship may receive centuries of Earth transmissions compressed into a much shorter period of onboard time during a high-speed approach. That sounds helpful, but the frequencies may shift outside the range for which the receivers were designed. A radio message originally transmitted at one frequency might arrive at another. The electronics must know where to look. The message also weakens as it spreads. Electromagnetic radiation expands across a growing area, so the energy received by a detector generally decreases with the square of the distance from the source. Double the distance, and the same transmitted power is spread across 4 times the area. Increase the distance by a factor of 1,000, and the received intensity falls by a factor of 1,000,000 before other losses are considered. Earth leaks radio energy into space, but much of that leakage becomes difficult to distinguish from natural background noise after travelling far enough. Modern communications also tend to use narrower beams and lower unintended emissions than early broadcast systems. The galaxy is not filled with a loud, clear announcement saying, "Earth is here." A deliberate beacon would be more useful. A powerful transmitter aimed toward the spacecraft could send timing signals, ephemerides, and instructions. The beam would need to know where the spacecraft was expected to be when the message arrived. A narrow beam conserves power by concentrating the signal, but it is easier to miss a moving receiver. A broad beam covers more uncertainty and becomes weaker. The transmitter faces the same outdated information problem as the traveller. Earth sees the spacecraft where it was when the incoming signal left it. Engineers must predict where it will be after the outgoing response crosses the distance. If the craft is 100 light-years away, a request takes 100 years to reach Earth. A reply takes another 100 years to return. 2 centuries pass in the Earth-based frame before the traveller receives the answer. The spacecraft does not remain where it sent the request. It may travel many light-years during the round trip. A reply saying, "Turn toward these coordinates," must be based on a predicted future position. If the ship altered course after sending the request, Earth may aim the response toward an empty region. Interstellar communication cannot work like a telephone call. It resembles sending instructions to someone who will read them generations later while moving through an uncertain location. The best messages would be designed to remain useful despite delay. They could include the frame in which the coordinates were calculated, the time of transmission, a full model of the solar system's predicted motion, uncertainty estimates, and a sequence of future reference positions. The receiver would propagate the model forward to its own current estimate of time. Even then, the message cannot describe events that happened on Earth after transmission. It cannot warn the traveller about a later change in the beacon, a new gravitational measurement, or an unexpected failure. New information must begin another long journey. The finite speed of information creates a boundary around every event. In relativity, light cones describe which events can influence which others. A future light cone contains the events that a signal sent now could eventually reach. A past light cone contains the events whose signals could have reached the observer now. Earth, as it exists at the traveller's present moment, may lie outside the traveller's past light cone. The traveller has no access to its current state because no light or message from that state has had enough time to arrive. There is no telescope powerful enough to overcome this delay. A larger telescope collects more light and resolves smaller details, but it does not make the photons travel faster. The traveller can improve the prediction, not obtain instantaneous knowledge. The same limitation applies to gravity. Changes in gravitational fields propagate at the speed of light. If a distant system changes, the new gravitational information does not arrive ahead of the light announcing it. Navigation must use the causal information available at the spacecraft's location. This point becomes especially important if the Sun experiences an unlikely but significant disturbance. A close stellar encounter, a major change in the local gravitational model, or an artificial alteration of Earth's orbit would not be known immediately. The traveller continues calculating with the earlier state until information about the change arrives. For ordinary returns across a few light years, the solar system is stable enough that prediction remains practical. Earth's orbit does not randomly move to another star. The difficulty is precision, not complete unpredictability. Across tens of thousands or millions of years, more changes become relevant. The orientation of Earth's axis shifts. Planetary orbits experience perturbations. The Sun evolves slowly. Nearby stars change the local environment. Human transmitters may no longer exist or may use unrecognizable technologies. A message sent at departure may describe a society, a planet, and a navigation network that are gone by the time the ship returns. Physics does not separate navigational delay from historical delay. Both come from the same finite signal speed. A traveller could receive a radio broadcast showing a familiar city, but the city and the broadcast may have changed centuries earlier. The coordinates remain tied to old infrastructure. The landing instructions refer to runways that no longer exist. For finding the planet, cultural information is unnecessary. For finding a particular home on its surface, it matters. Earth rotates once per day, travels around the Sun once per year, and changes geologically over longer periods. Continents move by centimetres per year. Over millions of years, that becomes hundreds or thousands of kilometres. A location defined by old latitude and longitude may still be calculable, because the coordinates rotate with Earth, but the physical landscape may no longer match. Coastlines move, mountains rise and erode, rivers change course, ice advances and retreats. A house does not survive a geological timescale with the dependable patience of a mountain, and mountains are not especially patient either. The traveller may find Earth while failing to find the surface location remembered as home. Light from Earth can reveal some of these changes, but only after the delay. If the traveller is 10,000 light years away, the surface being observed belongs to 10,000 years earlier. During the return journey, the visible Earth becomes progressively less outdated as the distance decreases. At 1,000 light years, the delay is 1,000 years. At 100 light years, it is 100 years. At 1 light year, it is 1 year. Near the orbit of Neptune, the delay is measured in hours. The map becomes fresher as home approaches. That allows a layered navigation strategy. Far away, the spacecraft targets the Milky Way and the predicted region of the Sun. Closer in, it identifies the Sun by spectrum, motion, and surrounding stars. Inside the solar system, it detects planets and updates their orbits. Near Earth, radar, optical tracking, and local transmissions provide precise guidance. The traveller does not need perfect knowledge from the beginning. It needs enough accuracy to enter the next region where better references become available. A ship that reaches within a few light years of the Sun has a much easier task than one trying to identify Earth from across the galaxy. The Sun becomes brighter. Parallax becomes larger. Planetary effects become more measurable. Within the solar system, the target can be observed repeatedly with much shorter delay. Corrections can be made before errors grow to interstellar scales. Messages also become more practical. At the distance of Mars, a one-way radio delay ranges from a few minutes to more than 20 minutes. That is inconvenient for direct control but manageable for planned operations. At the outer planets, delays become hours rather than years. Near Earth, communication begins to resemble ordinary remote guidance. The long silence is replaced by increasingly current information. The difficulty is reaching that communication region without relying on current information to get there. A robust return plan would therefore use autonomous navigation. The ship would not wait for Earth to tell it every correction. It would carry physical models, star catalogues, pulsar timing data, and the ability to update those models from observation. Earth's messages would serve as additional evidence rather than the only source of direction. Autonomy becomes essential because a command may arrive after the decision it concerns. A warning about an upcoming encounter is useless if the spacecraft passed the object 50 years before receiving it. The ship must make decisions using local data. One-way signals can still help establish distance. If Earth transmits a sequence stamped with emission times, the spacecraft can compare the arrival times with its clock, once clock relationships and frame corrections are understood. The signal's direction gives a line of sight. The Doppler shift provides information about relative radial motion. Multiple transmissions over time help constrain the trajectory. Signals from several known sources would be better. A network of transmitters spread across the solar system could allow the traveller to triangulate its position. The signals would still describe delayed states, but the geometry and timing could be modelled. Natural sources can form a similar network. Pulsars provide regular timing. Quasars provide stable directions. Stars provide local distances and motion. No single source solves the problem. Their combination can. There is a statistical character to the solution. The navigation system estimates which position and velocity best explain all the observed signals. It also calculates uncertainty. As the spacecraft receives more data, the uncertainty may shrink. If the observations disagree, the system checks whether a source changed, a sensor failed, or the model is incomplete. The result is not an oracle giving the exact current address of Earth. It is a continually updated prediction. That prediction can become extraordinarily accurate. Modern spacecraft navigation already achieves impressive precision by combining delayed radio measurements with orbital models. A future interstellar system could do far more. The phrase, "messages arrive too late," therefore does not mean messages are useless. It means they cannot replace prediction. Every signal is historical evidence. The navigation computer turns that evidence into an estimate of the present and a forecast of the future. Even a visible image of Earth must be treated this way. The planet appears where it was. The ship must travel toward where Earth will be. The difference between those two positions grows with distance, travel time, and uncertainty in the motion. A traveller could receive a final message from Earth shortly before entering the solar system. The message might still be months or years old. By the time the craft reaches Earth, the planet has moved around the Sun, the receiving stations have rotated with the planet, and weather has changed the conditions at the landing site. The route remains a prediction until the last stages of approach. Close-range sensors finally provide nearly current information. Radar echoes return quickly. Optical images are delayed by fractions of a second. Atmospheric navigation and local beacons can guide the vehicle toward a landing area. At that point, the interstellar problem becomes an ordinary aerospace problem, although arriving from another star is not a particularly ordinary way to begin it. The ship may reach the correct planet, enter orbit, and land safely. That would count as finding home in every practical sense. Still, it would not erase the delays, corrections, and uncertainties that shaped the journey. The craft did not return to a fixed point preserved from departure. It intercepted a later Earth after reconstructing its motion from old information. Once navigation depends on prediction rather than direct knowledge, the remaining question is not simply whether home can be found, it is how exact any return could ever be, and what the word exact is supposed to mean when the planet, the traveller, the clocks, and every surrounding reference have continued to change. Does an exact return mean reaching the solar system? Does it mean entering orbit around Earth? Does it mean landing at the same geographical coordinates from which the traveller departed? Does it mean touching the exact same patch of ground, with the spacecraft oriented in the same direction and every clock showing the expected time? Each definition demands a different level of precision. A spacecraft can miss Earth by 1 million kilometers and still be close enough to detect the planet, communicate with it, and perform a correction. It can pass through the inner solar system without coming near Earth at all. It can enter Earth orbit while remaining hundreds of kilometers above the surface. It can land successfully while touching the ground several meters away from the intended point. All of these results are different, but some would still count as returning home. Physics usually handles this by specifying a tolerance. A mission does not demand an infinitely exact trajectory. It defines an acceptable region of position, velocity, timing, and orientation. The spacecraft must arrive within that region. For a flyby, the target region may be relatively large. For orbital insertion, the allowed velocity and direction become more restrictive. For landing, the target shrinks again. A runway, landing pad, or safe surface area provides a finite zone rather than a mathematical point. This is fortunate because no physical measurement has infinite precision. A navigation system does not know the spacecraft's position as one perfectly exact set of numbers. It estimates a state. That state usually includes 3 position components and 3 velocity components, along with orientation, angular velocity, clock offsets, fuel levels, and other quantities. Each estimate carries uncertainty. The display may report a position to the nearest meter, but the true position could lie somewhere inside a surrounding range. Better measurements shrink that range. They do not reduce it to zero. Light arrives as individual photons. A detector counts them and records where and when they were received. When a source is faint, only a limited number of photons may arrive during an observation. The measured direction and brightness then contains statistical noise. Collecting light for longer improves the estimate because more photons are received. A larger telescope also helps. Neither produces an infinitely exact measurement, and a longer observation allows the spacecraft and the observed object to move while the data is being collected. The instrument must account for that movement. Detectors also produce electronic noise. Their temperature affects performance. Radiation damages components. Mirrors and antennas cannot be manufactured or aligned with perfect accuracy. A telescope may flex slightly as the spacecraft changes temperature or rotates. Calibration reduces these effects but does not remove every uncertainty. Clocks have limits as well. Atomic clocks are extraordinarily stable, yet their rates are not known with infinite precision. Temperature, magnetic fields, motion, gravity, and technical imperfections must be considered. A small clock error changes the inferred distance of a signal source because distance is often estimated from travel time. It changes the predicted orbital position of Earth. It changes the planned moment of an engine burn. Sensors measuring acceleration and rotation introduce their own biases. Engine burns differ slightly from their commanded values. A valve opens a fraction later than expected. Thrust varies during the maneuver. The spacecraft's mass changes as fuel is consumed. The navigation computer measures the result and corrects again. This repeated process can produce remarkable accuracy. It cannot produce mathematical perfection. The distinction matters because a perfectly exact return would require the traveller to know the initial conditions of the spacecraft, Earth, the Sun, and the relevant gravitational environment without any uncertainty. The traveller would then need a perfect physical model and perfect control over every manoeuvre. No real system provides all three. An inaccurate initial position produces an inaccurate prediction. An incomplete gravitational model produces a curved path that differs from the calculated one. A small propulsion error changes the future trajectory. Repeated observations can keep these differences within useful limits, but there is always another decimal place that remains unknown. The gravitational environment is not perfectly simple. Planets pull on one another. Asteroids and comets contribute smaller forces. Passing stars affect the solar system over long periods. The galaxy provides a broader field. A model can include the largest influences and many of the smaller ones. At some point, an object is too faint, too distant, or too poorly measured to include exactly. Its effect may be negligible for practical navigation. Negligible is not the same as zero. The solar system also exhibits sensitive dependence in some parts of its long-term behaviour. Planetary motion is highly predictable over ordinary mission timescales, but exact orbital phases become less certain when calculations are extended far enough into the future. This does not mean planets start moving randomly. Their motion remains governed by physics. It means tiny uncertainties in initial conditions grow, limiting how far an exact prediction can be extended. A traveller returning after 20 years faces a much easier prediction than one returning after 20 million years. The longer interval gives small uncertainties more time to affect the result. An ancient spacecraft may still find the Sun because the general galactic orbit remains constrained. Determining the exact location of Earth on a particular future date requires far more detailed information. Close observations can replace long-range prediction once the spacecraft approaches. That is why perfect predictions are unnecessary for a practical return. The ship only needs to predict well enough to get close, then measure again. Suppose the vessel reaches the outer solar system with an uncertainty of several million kilometers. That sounds enormous, but the Sun is easy to detect from that distance. The spacecraft can update its position using the Sun, planets, and local radio sources. The uncertainty shrinks. Near Earth, radar and optical tracking provide more precise measurements. The ship calculates a new trajectory. Atmospheric entry sensors supply further updates. Navigation progresses from broad estimates to local corrections. The traveller does not throw one perfect dart across the galaxy. The traveller makes a long sequence of imperfect measurements and corrections. That is how navigation works on Earth as well. A driver follows a road, checks signs, notices turns and adjusts. A pilot uses instruments, beacons, satellite data, and visual references. Nobody expects the vehicle to maintain a flawless trajectory from departure without new information. Deep space extends the interval between useful references and magnifies the cost of every error. The final approach introduces new uncertainties rather than eliminating them. Earth has an atmosphere, and the atmosphere changes. Air density varies with altitude, temperature, solar activity, latitude, season and weather. A returning spacecraft moving at high speed encounters drag and heating. Small differences in the atmosphere change the path. Winds shift the vehicle sideways. Clouds interfere with visual sensors. A storm may make the planned landing site unsafe. The ship can adapt, but the precise landing point may differ from the one predicted before atmospheric entry. A perfectly exact touchdown would require perfect knowledge of turbulent air, surface conditions, vehicle response, and every small force during descent. The atmosphere has shown no willingness to provide that service. Even a vehicle landing in a vacuum cannot control its position infinitely well. Thrusters operate in finite pulses. Sensors have finite resolution. The ground may contain loose material that moves under the exhaust. Landing legs flex. Practical engineering chooses acceptable error margins. A spacecraft arriving within those margins has succeeded. At a deeper level, quantum mechanics places fundamental limits on how precisely positioned and momentum can be specified together. The more precisely one quantity is known, the more uncertainty remains in the other. For a large spacecraft, this quantum uncertainty is unimaginably smaller than the ordinary errors caused by clocks, sensors, gravity models, and propulsion. It would not be the reason a ship misses Earth by 1,000,000 kilometers. It still means that infinitely exact knowledge of the spacecraft's state is not available even in principle. Macroscopic objects also interact constantly with their environment. Photons strike the hull. Thermal radiation leaves it. Dust particles collide with it. Internal atoms vibrate. The spacecraft is not a perfectly isolated point following an exact line. None of this prevents accurate travel. It prevents the word exact from meaning unlimited decimal precision. There is another reason the traveller cannot return to the same place in the fullest physical sense. The original departure was an event in space-time. It occurred at one location and one time. The spacecraft may later return to the same geographical coordinates, but it cannot return to the same event without travelling into the past. Ordinary forward travel brings it to a later event on Earth's world line. The spatial coordinates may match in an Earth-fixed frame. The time coordinate does not. This is similar to returning to the same seat in a theatre on another evening. The number on the seat is unchanged, but the event is different. The audience has changed, the air has changed, and the performance is later. A location without a time does not completely specify an event. The traveller can return to Earth. The traveller cannot make the return erase the journey. Relativity makes the difference measurable. The traveller's clock may show less elapsed time than clocks on Earth. The route through velocity and gravity determines how much proper time each experiences. The crew might feel that only a few decades passed while centuries passed at home. Both elapsed times are physically valid for the paths followed. Landing does not synchronize the histories. It merely brings the worldlings together again so the clocks can be compared. Even the exact surface location may not remain physically unchanged. Earth's crust moves. Tectonic plates carry continents across the mantle. A point fixed to one plate can shift, relative to the planet's centre and rotational axis. Over a few years, the motion may be measured in centimetres. Over millions of years, it becomes large enough to rearrange oceans and continents. Erosion removes material. Sediment adds new layers. Earthquakes shift the ground. Volcanic activity creates and destroys terrain. Sea level changes. The remembered place may now lie beneath water, ice, rock, or a different landscape. Latitude and longitude can still identify a direction from Earth's centre, but the physical material occupying that direction changes. A traveller looking for the same atoms would face an impossible task. The atoms in a house, a road, or a body are constantly exchanged with the environment. Paint flakes away. Water evaporates. Plants grow. Buildings are repaired or demolished. Human bodies replace much of their material over time. Home is not a permanently sealed collection of matter. For navigation, none of that matters. The ship can land at the intended coordinates. For the claim of returning to exactly the same physical place, it matters greatly. The planet itself also changes its orientation. Earth's axis precesses. The length of the day changes gradually. The moon moves farther away. Planetary perturbations alter the orbit. A landing system using ancient models would need to update all of these quantities. The same coordinate label may refer to a different orientation in space if the definition is not maintained carefully. Modern reference systems already account for movement. Survey coordinates are updated for tectonic motion. Earth orientation parameters track changes in rotation. High-precision navigation treats the planet as a moving, deforming body rather than a perfect, rigid sphere. An interstellar return would need the same approach over a much longer interval. Suppose the traveller succeeds. The ship identifies the Milky Way, locates the Sun, enters the solar system, finds Earth, matches its orbit, survives atmospheric entry, and lands within a few meters of the departure site. From an engineering perspective, that is an extraordinary exact return. From a mathematical perspective, it is not perfect. The arrival time differs from the departure time. The spacecraft's microscopic state differs. Earth has moved through the galaxy. The surrounding matter has changed. demanding more precision would not change the practical meaning of the success. This is why the phrase, "you could never find your way home," needs a careful conclusion. Physics does not say that every lost traveller must wander forever. A sufficiently capable spacecraft could return if it retained enough information, remained within a causally reachable region, possessed suitable instruments and propulsion, and had time to make observations and corrections. The difficult word is lost. If the traveller knows the departure time, the initial trajectory, and the correct reference frame, the problem is navigation. If those records are damaged but recognisable stars and signals remain, the problem is reconstruction. If every connection to the original map is gone, no instrument can obtain the missing history simply by measuring nearby space. The traveller may determine the local position relative to surrounding stars and still be unable to identify which one is the Sun. A physical state does not contain a label saying where it came from. Two regions of the galaxy could produce similar local observations. More distant measurements might distinguish them. Without enough information, several possible locations may remain consistent with the data. Choosing one would be an estimate, not certainty. The spacecraft could search. It might travel toward the most likely region, collect new observations, and revise the decision. The search area could be enormous. During the search, the solar system continues moving. The term never becomes justified only under stronger conditions. Home may lie beyond a cosmological horizon. The spacecraft may lack enough energy to change its trajectory. The identifying records may be gone, and no detectable signal may connect the local sky to Earth. The traveller may also be so late that Earth no longer exists in its familiar form. The Sun gradually becomes more luminous as it ages. On timescales of billions of years, this changes Earth's climate. Several billion years from now, the Sun is expected to enter later stages of stellar evolution and expand into a red giant. A spacecraft returning after such an interval would not find the present solar system waiting unchanged. The destination would have evolved. For any plausible human interstellar journey, these stellar timescales are far beyond the immediate concern. They show that home is not physically guaranteed to remain available forever. The same applies on shorter scales in less dramatic ways. Civilizations change, transmitters stop, languages disappear, surface landmarks are replaced. The planet may remain, but the traveller's operational definition of home may not. Physics can guide the ship toward a world line. It cannot preserve every condition associated with departure. That is the clearest meaning of a return that is never perfectly exact. The traveller does not recover a fixed coordinate from a motionless universe. The traveller meets a later version of a moving planet. The route begins by choosing a reference frame. It continues by identifying stars that have changed position. It accounts for the spacecraft's inertia, the growth of tiny errors, and gravity's effect on every path. Relativity translates between clocks and maps that disagree about space and time. Galactic motion carries the solar system away from its earlier coordinates. Cosmic expansion changes distances between unbound galaxies. Delayed light shows where objects were, while navigation requires where they will be. None of those facts makes useful navigation impossible. Together, they remove the simple idea of turning around and following the same line home. There is no line waiting in space. The ship must build a route from measurements, models, and corrections. It must identify the destination repeatedly. It must predict, observe, and revise. The closer it gets, the better the information becomes. A faint stellar candidate becomes the Sun. A small periodic signal becomes evidence of planets. A pale point becomes Earth. Radio messages become current enough to use. Planetary motion replaces galactic uncertainty. Eventually, the spacecraft may enter orbit and look down at oceans, clouds, and continents. The planet is not where it was when the journey began. It is not at the same point in its orbit, the same point in the galaxy, or the same moment in history. It is still Earth. That is the practical answer. Home can be found without being perfectly recovered. Perhaps you're listening from home tonight, in a room that seems fixed and quiet. Since this journey began, Earth has rotated, moved along its orbit and travelled farther through the Milky Way. The room remained useful as a location because everything nearby shared that motion. Where are you listening from, and what time is it there now? Those ordinary details are enough to locate you within daily life. They work because a large network of clocks, maps, roads, satellites, and shared agreements keeps the answer meaningful. Remove that network, travel far enough, and even the question, "Where am I?" becomes a physics problem. If you found this long journey relaxing or useful, you can support Science for Sleep with a like and a subscription. It helps these slower explanations reach other listeners who enjoy letting the details settle without being rushed. For now, there is no course correction to calculate, and no galactic reference frame to rebuild. Earth is already beneath you, moving exactly as it has been throughout the entire journey. You do not need to find the way back tonight. Sleep well wherever on the moving planet you happen to be.